Okay, now we're going to do doubly linked lists. And in this video, we're going to create our constructor. So I'm going to start by bringing up a singly linked list. A doubly linked list is just going to have arrows that also go the other way. So the first thing we need to do, just like we had with singly linked lists, is we need to create a node. So I'm going to start out with a singly linked list node like this. And remember, that looked like this. And in the constructor, we had self.value and self.next in order to create this. So our constructor looked like this. So for a doubly linked list, we just need one more line like this. We're going to call this previous. It will be set to none because this node is not pointing at anything yet. And that's the only difference in creating the node. So that is going to build something that looks like this. So now that we can create nodes, let's start building our doubly linked list class. So we're going to start this class out by creating a constructor. And we're going to pass this a value so we can create the first node in the doubly linked list at the time that we create the doubly linked list. And we'll create that with this line of code, and we'll pass it a value. And notice this line of code is identical to the one we used to create a node in a singly linked list. The only difference is the node class that we're calling here also includes previous. And then we'll say self.head equals new node, like that. Self.tail equals new node, and that does that. And then we'll say that the length is 1. So we'll create a new doubly linked list by doing something like this. My doubly linked list equals doubly linked list. We pass it the value 7, and this line of code is going to create all of this. We have a head and a tail, and we have a node with a value of 7, and the length is equal to 1. Now let's go look at this in VS Code. So up here, we have our node class with value next and previous. I'm just going to scroll this up. And this is where we create the doubly linked list class. Here's our constructor. And then I also have a method here called printList, just like we did in singly linked lists. And we'll use this to be able to look at our linked lists. So down here, we have that line of code that we just saw, which is my doubly linked list equals doubly linked list. We're going to pass it a value of 7. And then when we come down here, we'll print the list, and we should just get that node with a value of 7. I'm going to run this, and there's our value of 7. All right, it looks like we have created a working constructor. Okay, so let's do our append method. And I'm going to start by bringing up our singly linked list. And when we added an item with a singly linked list, we just pointed this arrow over, moved tail over, and that added it into the list. When we have a doubly linked list, the only difference is we have these arrows going the other way. And the only difference in the append method is going to be that green arrow that is pointing back from the node that we're appending. So we'll have this go across. That's all the same. The new thing is having this come back, and we still have tail move over, and that adds that into the list. And we're still going to have to code for this situation when we don't have any items in our doubly linked list, and then we'll have head and tail point to that new node. So if you want to code this, pause the video here. Otherwise, we'll move forward with the code. So we'll call our method append. We're going to pass it a value, and we'll use that value to create a new node. We'll pass that value to the node class, and that creates our node. So the first thing we'll code for is this situation when we have an empty linked list where we have head and tail point to the new node. We have to test to see if the linked list is empty, and we'll do that like this. If head is none, then we'll have head be set equal to the new node like this, and tail will be set equal to the new node like this. Let's add this in with the rest of our code. And of course, the other possibility is that we do have items in our linked list. So we'll say else, and we'll build out our else statement. So we'll say tail.next equals new node. That is tail.next equals new node, like that. And node.previous equals self.tail. In other words, that previous arrow on the new node is going to point to the same node that tail is pointing to, like this. Then we'll set tail equal to new node. That moves tail over and adds that item into the list. So now let's add this in with the rest of our code. And the only things left to do are to increase the length by 1, and then we will also return true. So just like we did in singly linked lists, we're going to use the append method in the insert method, and the insert method requires a Boolean to be returned. So we're going to return a Boolean here so it can be used in the other method. So that is our code for append, and we'll look at this in a moment in VS Code. And when we do, we're going to initialize the linked list with a node with a value of 1, and we will append another node, so the linked list will contain 1 and 2. So now let's flip over to VS Code. So there is our append method there, and this is where we initialize the linked list with a 1 and append a 2. And then down here, we'll print out our doubly linked list. Okay, so I'll run this. And you can see up here that this printed out a 1 and a 2. So we have a working method for append. So if you recall from singly linked lists, to move tail to the left was an O of N, because you're moving tail to the left when all of the arrows are pointing to the right. So in order to do that, you had to start at the head and iterate through the entire list to get to this point. But with a doubly linked list, we don't have this problem. We do have arrows pointing to the left, so this is going to be much simpler with a doubly linked list. Now let's walk through the steps to pop that item off the end. So the first thing, since we're going to return it, we need to have a variable pointing to it that we'll call temp. And the next step is to move tail over, and we just say tail equals tail.previous, and that's going to move that over. Then we need to break the connection between the two arrows that are between that 7 and 4 node. So the first one will say tail.next is none, that breaks that one. And then we'll say temp.previous equals none, and that breaks that off. And then we can return temp. We do have a couple of edge cases here, one for if we only have one node in the list, and another one for when we don't have any nodes in the list. Okay, so those are the steps. If you want to try to code this, go ahead and pause it here. Otherwise, I will get into the code. And we will code for this situation first when we don't have any items in our doubly linked list. So we'll say pop, and we'll say if the length is 0, we're going to return none. So let's remove this code. And now let's look at if we have 2 or more items. First, we'll create that temp variable. Temp equals self.tail, like that. So we'll say tail equals tail.previous, and that moves that over. Then we'll say tail.next is none, and that breaks that connection. And we'll say temp.previous is none, and it breaks that connection. And then we'll decrement the length by 1. So let's look at this in with the rest of our code like this. So if you'll recall from the pop method in singly linked lists, we had an edge case for if we had one item in the list and we pop that off. And we're going to handle it with this code here. I'm not going to walk through all of the detail here because we walked through this in detail in that video for pop in singly linked lists. But we're going to say if the length is 0, we need to set head and tail to none. And this is the length being set equal to 0 after we decrement it here. And then we will return temp. So this is very similar to the code that we wrote for singly linked lists for pop. And I walked through the code in a particular order in that video because I wanted to teach particular things. But in this video, what I want to do is clean this code up. The problem I have with this code is we have if self.length is equal to 0 here, and then we have it again down here. And yes, this one is after we decrement the length by 1, but this is not as readable as it could be. So what I'm going to do is I'm going to take this if statement and everything inside of it, and I'm going to move it up. In order to do that, I'm first going to remove 5 lines of code out of this, and I will bring all 5 lines back in a moment. We're just going to rearrange this. So first I'm going to remove those 5 lines of code, and when I move this up, because this does represent the situation where you start with one item, I'm going to change that 0 in the if statement to a 1. Then I'm going to say else, and we have these 3 steps again, and decrementing the length, and returning temp. So those are our 5 lines of code that I've brought back. But let's look at how much more readable this is now. This is if we have 0 items. This is if we have 1 item. Then this is for 2 or more items. There is 1 line of code that I've added here, and that's actually the else, and that's it. So now let's take this code here and change it back to the way it was. It is exactly the same lines of code, just rearranged, and much easier to read. So we're going to look at this code in a moment in VS Code, and we will create this linked list. And this allows us to test all 3 of our scenarios to see if we can pop an item off of a list with 2 or more items, and we'll pop that off, and then see if it works with a list with 1 item. And then we'll run it again to see if it works when we don't have any items in the linked list. Okay, so let's flip over to VS Code. And there is our pop method there. And this is where we create our doubly linked list with the items 1 and 2. And this is where we print that out. So let's just run this. And you can see up here that this returns 1 and 2. So what I'm going to do here is I'm going to scroll up. And I'm going to take this print statement here, this print list. I'm going to remove this. And I'm going to paste in these lines of code. So all we're doing here is running pop 3 different times. We're running it for when we have 2 items, and for 1 item, and then for 0 items. All right, so let's run this. So that's going to return 2 nodes and then finally return none. And as we have done before to test this, I'm going to say return temp.value instead of returning the entire node and run this again. And that returns 2, 1, and none, which is exactly what we're looking for. And then always remember to come back up after you've tested it, remove value, so it just returns temp because you want it to return the entire node. So it looks like we have a working method for pop. Okay, let's do prepend. We'll bring up our doubly linked list here. So for prepend, we're going to have 3 steps. We're going to have new node.next point there. We're going to have this other arrow point back. We move head over, and that adds that into our list. And of course, you have to code for when you don't have any items in the list, in which case we have head and tail point to the new node. Okay, so those are the steps. If you're going to code this, go ahead and pause it here. Otherwise, we'll get into this. So we'll say prepend. We're going to pass it a value so we can create the node that we're going to prepend to the list. And that creates our node. And the first situation we'll code for is when we don't have any items in the list. And we'll say, if the length is 0, we'll have head and tail point to the new node, like that. And the other possibility is we have a linked list with items in it, so we'll say else, and we'll build out our else statement. So the first thing we're going to do is have the next pointer on the new node point to the same node that head is pointing to, like this. We'll do that with this line of code. New node.next equals self.head, and then we'll have the pointer from the 11 point back at the 4 node, like this. That is head.previous equals new node. We'll do that with this line of code, head.previous equals new node. Then we just need to have the head point to the new node. And we'll do that with this line of code, self.head equals new node. And that adds that into our list. So let's add this code in with the rest of our code like this. Then we just need to increase the length by 1. And then we're going to return true. And that is our code for prepend. And we'll look at this in a moment in VS Code. We will build this linked list with a 2 and a 3. And then we will prepend a node with a value of 1. And we should have a linked list with 1, 2, 3. Okay, so let's flip over to VS Code. So there's our prepend method there. And this is where we create our linked list with the 2 and the 3. And we'll print that out with this line here. And I'll run this. And that gives us a 2 and a 3. So what I'm going to do is I'm going to scroll up a little bit here. And in between the creation of this linked list and this print list, I'm going to paste this line of code here, which is going to prepend the number 1 to our list. And then we'll print it out and we should see 1, 2, 3. So I will run this. And now that has returned 1, 2, 3. Okay, and that is our method for prepend. Okay, so now let's do pop first. So I'll bring up our doubly linked list here, and pop first is just removing that first item. We do have two edge cases. First is if we have only one item in the list, and the second one is if we don't have any items in the list. So if you're going to code this, go ahead and pause it here. All right, so we'll start it like this, and we will start with this scenario first where we don't have any items in the linked list. And we'll say if the length is 0, we'll return none. So the second scenario we have is if we only have one item in the linked list like this, and it doesn't matter if we have one item like this or if we have two or more. We're going to need the temp variable to point to the head. We'll do that like this. And for this scenario, we're going to say if the length is 1, we'll have head and tail point to none, like that. And now let's look at what we have so far with our code. This is for if we have 0 items in the list. This is if we have 1. And now let's look at if we have 2 or more. So we'll say else, and we'll build this out. We'll bring this up. And remember, we've already set temp equal to head. So to remove that item, the first thing we're going to do is we're going to set head equal to head.next. With this line of code, head equals head.next, and that moves that over. Then we're going to say head.previous is none, which does that. We do that with this line of code, head.previous equals none. Then we'll say temp.next is none, and we'll do that like this. Temp.next is equal to none, and that removes that from the list. So let's look at this code and with the rest of our code. And the only things left to do are to decrement the length, and then we'll return temp. And that's our method for pop first. We'll look at this code in a moment in VS Code, and when we do, we'll create a doubly linked list that looks like this. This way we can test all 3 of our scenarios for having 2 or more items on the list, and we'll see if pop first works in that situation, and for 1 item in the list to see if that works, and then we'll run it again to see if it works when we don't have any items in the list. All right, so let's flip over to VS Code. So there's our pop first method. This creates our linked list with the values 2 and 1 that we just saw, and this is going to print that out. So let's run this, and that prints out our linked list with 2 and 1. Okay, so what I'm going to do is I'm going to scroll this up, and then I'm going to remove this line here where we print the linked list out, and I'm going to replace it with these 3 lines of code. And all we're doing here is running pop first 3 times in a row, once for when we have 2 items, and then 1 item, and then for 0 items. So I'll run this, and that returns our 2 nodes and returns none. And just to make sure this is all working correctly, I'm going to come up here and change this to temp.value, and then run this again. And that has removed our 2 node, then our 1 node, and then return none when our list was empty. And as we usually do, we're going to come up here and remove the .value, so it just returns a node instead of just the value. All right, and that is our method for pop first. Okay, let's create our get method. And get is going to look like this. We're just going to get an item at a particular index. So as we've been going through these methods for doubly linked lists, you may have noticed that some of these are essentially the same as the methods for singly linked lists. The big exception to this point has been pop, and that one's very different in doubly linked lists versus singly linked lists. Get is going to be one of those methods that we write very differently than the way we did in singly linked lists. So let's start out by actually bringing up a singly linked list and walk through the steps that we went through to make this work in a singly linked list. First, we had to make sure our indexes were, in this case, 0, 1, 2, or 3. We couldn't have anything out of range on this end, and we couldn't have anything out of range on this end. So we would say if the index is less than 0 or greater than or equal to the length, then we're going to return none. This is going to be the same in a singly or doubly linked list. So let's bring up our linked list here. And what we did is we set temp equal to head, like this, and we'll remove head and tail. And we created a for loop to go until we got to the index. And we would move temp forward by saying temp equals temp.next until we got to the index that we were looking for. And then we would return temp. So this was our code for the get method for a singly linked list. And it just so happens this all works just like this for a doubly linked list. But in a doubly linked list, we can optimize this. So let's bring this up, turn this into a doubly linked list, and look at a couple of scenarios. First, let's return the item at the index of 1. In this situation, we're going to start at the head, and we're going to iterate through until we get to that index, and then we can return that node. But if we're looking for the node at the index of 2, it would be more efficient to start at the tail and go the other way. It's closer to tail than it is to the head. So if we're going to optimize this for a doubly linked list, there are some changes that we need to make. So let's bring our code back and make our changes to this code. So you only want to do this for loop here if the item you're looking for is in the first half of the list. So we're going to say if the index is less than self.length divided by 2. In other words, it's in the first half of the list. Only then do we run this for loop. So if it's not in the first half of the list, it's in the second half, obviously. So we'll say else. And let's shrink this down a little bit here so we have more room. And the first thing we need to do here is set temp equal to the tail. In other words, temp was here, but in this situation, we need to start here and move backwards through our doubly linked list. Then we need to create a for loop that's going to start at this point and go backwards. And we do that like this. So what we saw in the other for loop is we just passed it an index. But what you can also do with a for loop is you can tell it the number where you would like to start. In this case, the length minus 1, in other words, the index of 3. Normally, when you have a for loop, you just want it to increment by 1 every time you loop through. In this case, we can tell it to decrement by 1 every time we loop through. And as we do, we'll say temp equals temp.previous, which is going to move that to the left. And once we get done running through our for loop, we'll return temp, which will return that node that we're looking for. So let's look at this with the rest of our code. We'll look at this in a moment in VS Code. We'll create this doubly linked list, and we'll run the get method at the index of 1, which will return the value of 1. And then we'll run it again at the index of 2, which should return the value of 2. But this is going to test to make sure that our code is working that goes backwards through our doubly linked list. All right, so let's flip over to VS Code. So there's our get method there. And this is going to create our doubly linked list with 0, 1, 2, and 3. And then we'll print this. And there's our linked list with 0, 1, 2, and 3. All right, so I'm going to scroll up here, and I'm going to replace this print list down here. And then we're going to get the item at the index of 1, and we're going to get the item at the index of 2. And I'm going to go ahead and change this to dot value before we run this. Of course, we're going to change this back when we're done testing this. And I'll run this. And you can see up here that we have returned 1 and 2. So I'll remove the dot value up here, and that is our method for get. Okay, let's do our set method. And remember, set is actually a keyword in Python, so I called mine set value. We pass it an index, and then we change the value of the node at that index. So if you want to code this, pause it here. Otherwise, I will get into this. So we'll bring up our doubly linked list like this. So the first thing we have to do is have a variable that's going to iterate through this list and get to the node that we're going to change. If we're going to change the node at the index of 1 from a 3 to a 4, we have to get temp over there. And I'm just going to change this back to a 3 for now. But just like with a singly linked list, we're going to do it like this. Temp equals self.get, and we're going to pass this an index, and that's going to have temp point to the correct node. Now this code looks the same, but remember the get method is written differently for a doubly linked list. We have that efficiency where we can start at the other end and go backwards if it's in the second half of the list. So the get method is going to do one of two things. It is either going to have temp point to the node that we're looking for, or it is going to return none because the index is out of range. So we have to test this with an if statement to see is temp equal to none, or is it pointing at a node. So we'll say if temp, and you could do this as if temp is not none, temp.value equals value, the value that we pass the set value method. In this case, we pass it a 4, and that's going to update that 3 to a 4. And then we'll return true that we were able to change this. So if temp is not pointing to a node, the condition in the if statement is going to be false. We will skip that, and then we're going to return false. And that is our set value method. And this is the first one in doubly linked lists where there isn't a single line of code that is different from the singly linked list to the doubly linked list. There's a difference in how this will run because the get method that we're calling is written differently. But as far as the actual code, this is identical. So we'll look at this code in a moment in VS Code. We'll build this doubly linked list, and we'll change that value from a 3 to a 4. All right, so let's have a look at this in VS Code. So there's our set value method, and this creates that linked list with 11, 3, 23, and 7. And this is going to print that list. So let's run this. And there is 11, 3, 23, and 7. So I'm going to come down here, and in between our creation of our linked list and our print list statement, I'm going to paste in my doubly linked list, and then we're going to set value at the index of 1 and change it to a 4. And then we'll print the list again here, and this should be 11, 4, 23, and 7. So let's run this. And there is 11, 4, 23, and 7. All right, that is our method for set. Now let's do our insert method. With insert, we are going to insert at a particular index a new node with a particular value. So if you want to code this, go ahead and pause it here. Otherwise, I will get into the steps for coding this. All right, here's our doubly linked list, and we're going to create a new node. And when we insert this, obviously we can't have an index less than 0. We can't have an index that is greater than the length. So we'll say if the index is less than 0 or the index is greater than the length, we're going to return false. We can also insert this at the index of 0. If it's at the index of 0, we'll just return self.prepend and pass that the value, and that will put that on that end of the linked list. And then also on the other end, if the index is equal to the length, we'll return self.append and pass that the value. So let's take a look at all 3 of these if statements like that. And now let's look at adding this somewhere in the middle. In order to do this, we'll need a couple of variables. We'll create one called after that points to the node that will be after this one, after we insert it, and then before. These will go before and after the new node after it is inserted. Now let's create all 3 of these. First, the node. Then we'll create our before variable, before equals self.get at index -1. And then after, we don't want to use the get method here because we can say after equals before.next. The get method is O of n. It has to iterate through the linked list. Whereas if you do it like this, it's O of 1. So let's add these 3 in with the rest of our code like this, and we'll bring back our doubly linked list. And I'm just going to take this and spread this apart so we have room for our new node to go in there. And what we're going to need to do is redirect these 4 arrows. And when we're done, we want them to all look like this. So let's put this back, and we'll start with the 2 arrows that are on the new node. We'll say new node.previous equals before. That is to say, the previous arrow on the new node is going to point at the same node that before is pointing at, like this. Then we'll say new node.next equals after. The next arrow is going to now point to the node that after is pointing to, like this. Then we'll say before.next equals new node. And then after.previous equals new node. And that adds the new node into the list. So these 4 lines of code redirected these 4 arrows. Now let's look at this end with the rest of our code like this. Then we just need to increase the length by 1, and then we'll return true. So that is our insert method. We'll look at this in a moment. And when we do, we'll create this doubly linked list with 1 and 3. We'll print that out. And then we'll run an insert method to insert at the index of 1 a node with the value of 2. And then we'll print it out again, and it should print out 1, 2, 3. Okay, so let's flip over to VS Code. There's our insert method there. I'm going to scroll up. And this creates our doubly linked list with values of 1 and 3. And then with this line, we will print that out. So let's run this. And that has printed out 1 and 3. And then between these two, I'm going to paste this line of code, which is going to insert at the index of 1 a node with the value of 2. And then when we print this out here, we should get 1, 2, 3. So I'll run this, and that has printed out 1, 2, 3. All right, that is our method for insert. Now let's do our remove method. That's just removing an item at an index. So if you want to code this, go ahead and pause it here. Otherwise, we'll get into this. And there's our doubly linked list. Obviously, we can't remove an item at an index out of range. So we'll say if the index is less than 0 or the index is greater than or equal to the length, we're going to return none. And then if we remove the first item, we've already created a method for this. We'll say if the index is 0, return self.pop first. And likewise, on the other end, we'll say if the index is equal to the length minus 1, return self.pop. So let's look at all 3 of these, and then we'll bring back up our doubly linked list. So we're going to remove the item at the index of 2. And since we're going to return that, we need to have a variable point to it, and we'll use temp. And I'm going to show you a couple of different ways of doing this. One way you could do it is create before and after variables. And when you remove temp, you can say before.next equals after, and you can say after.previous equals before. And personally, this is how I would write this because I think it would be easier to read. But I'm not going to do it this way in this video because I want to show you a different way that you can do this. So I'm going to bring this back, and we are only going to use the variable temp. And we'll create that by saying temp equals self.get. Let's look at this in with the rest of our code. We're going to pass that get method the index where we want temp to point. Now let's bring back our doubly linked list. So I'm going to pop this 23 up here. And the way we're going to do this is those 2 arrows that we redirected before with a before and after variable are these 2 arrows. And we did this with them. We can do this by just using the temp variable. And we're going to do it like this. Temp.next.previous. That's the first one. You can represent that by saying temp.next.previous. We're going to set that equal to temp.previous. And the code looks like this. Temp.next.previous equals temp.previous. And that points that down here. And then we do that on the other side. We say temp.previous.next equals temp.next. And that looks like this. Temp.previous.next equals temp.next. And that points this down here. And as I mentioned before, I think doing it this way is harder to read. I would do it the other way, but I wanted to show you another way of doing this. Now we need to have those 2 arrows stop pointing at nodes in the linked list. We'll do that like this. Temp.next equals none, and temp.previous equals none. And that does this. And that removes that from our list. So we can remove our list now, and we'll decrement the length by 1, and then we'll return temp, which returns that node. So let's look at this code in with the rest of our code, like that. And we'll look at this in a moment in VS Code. And we'll build this doubly linked list, 0, 1, 2. We'll remove the item at the index of 1, and we'll be left with a list with values of 0 and 2. Okay, so let's flip over to VS Code. So there is our remove method there, and I will scroll up. This is where we create our doubly linked list with values 0, 1, and 2, and this is where we will print that out, and I'll run this, and that has printed out 0, 1, and 2. So in between these, now I'm going to insert this line of code. I'll paste that in, and we are going to run my doubly linked list.remove with a value of 1. Then I have a line break there, and then we're going to print out our list again. Okay, so let's run this. Okay, so this has returned our node, and it's returned 0 and 2. So let's come up here and do temp.value to make sure this is returning the right value, and we'll run this again. And it's returning the 1 node, and then our doubly linked list now contains 0 and 2. So we'll come back up here and remove the .value. And now that will return the full node. All right, and that is our method for remove. Now let's look at stacks. So my favorite analogy for a stack is a can of tennis balls. Let's go ahead and remove these, and I'll add one back. This is pushing an item onto the stack. And then of course we can push a second one onto the stack. But the thing that makes a stack is you can only get to the last item that you pushed onto the stack, that second tennis ball. As soon as you push that second one on, you can't get to the first one without first removing the second one. And then when we push the third ball on, we can't get to the second one. The only one we can get to is the one that is on top. This is called LIFO, last in, first out. So after we remove that third ball, it is only now that we can get to the second one, and then we can get to the first one. So let's look at an example of where you might use a stack. Let's say we have a web browser, and we go to Facebook. And then after that, we go to YouTube, and then we go to Instagram, and then we check our email. What we have created to the right of this computer screen is a stack of all of the previous websites that we have visited. So when we hit the back button, we are popping an item off of the stack. And it is only by removing that item that we can hit the back button again and get to the next item, and so on. So there are a couple of common ways of implementing a stack. First is to use a list. So for something to be a stack, you just have to add and remove from the same end. So if you're going to use a list, there's one end that you want to use for your adding and removing. And the reason for that is if you add on this end or remove on this end, it is O of 1, as opposed to the other end where if we're going to take this item and remove it, we have to re-index everything after it. And then when we bring it back, it's the same thing. We have to re-index to bring this back. So whether you are adding or removing from this other end, it's O of n. So if you're going to use a list to implement a stack, you want to make sure that you are doing your adding and removing from the other end. Except, of course, the stack would look something more like this conceptually. You would pop an item from the stack like that, or push the item on. That's the terminology for adding and removing. And this is probably the simplest way to implement a stack. We're going to do something a little bit more complex to give ourselves a little bit more of a challenge. We're going to implement it using a linked list. And we're going to implement our stack where it looks like this. What you don't want to do is implement a stack where the none terminated end is this way. And let's have a look at why. When you remove an item from the end of a linked list here, it is O of n. Adding it is O of 1 versus the other end where removing and adding are both O of 1. So that is why your stack should go this way and not the other way. So let's put this back for now. When we implemented a linked list, we had a method called pop first to remove the first item. We'll do something similar to pop an item from the stack. And then likewise, we had prepend. We can use something similar to that to create our push method to push an item onto the stack. So those two will be repurposed to become pop and push. Now with a linked list, we had head and tail. With a stack, we'll call this top and bottom. But with a stack, we're only adding and removing from the top. So we really don't need bottom. So our stack is going to look like this. All right, that is our overview of stacks. So now let's build our stack constructor. So the nodes that we're going to use will be identical to linked list nodes. And the linked list nodes look like this, and the constructor look like this, and we don't need to make any change here. So now let's build out the stack class. So we'll start our constructor like this. We'll pass it a value so we can create the first node in the stack with that value, like that. And in the linked list, we had head and tail set equal to the new node, like this. Well, in a stack, you would have this be top and bottom. Except with a stack, because you're only adding and removing from the top, you don't have to keep track of what's happening at the bottom, so we can remove that. And then we will also keep track of the height. And now we have initialized our stack. But visually, we'd want to point the arrow down like that. So let's go look at this in VS Code. So there's our node class there. And this creates the stack class here. That's our constructor for the stack. And then I've created this method called print stack. This is just like what we saw with print list for singly linked lists and doubly linked lists. This is almost identical. So we'll create a new stack here called myStack. We'll pass it the number 4. And then down here, we will run myStack.printStack. And that should print out the number 4. So let's run this. And there is the number 4. All right, so it looks like we have a working stack constructor. Now let's create our push method. And push is going to look like this. And we're going to push a new node onto the stack, and we'll have top point to that new node. And we'll be able to borrow heavily from the prepend method for linked lists. And just as we had in prepend, we have to code for when we don't have any items in the stack. So those are the steps. If you want to code this, go ahead and pause it here. Otherwise, I will get into the code. So we start this out like this. We're going to say push. We're going to pass it a value. We'll use that value to create a node. And there's our node. So we'll code for an empty stack first. We'll say if the height is 0, like this, we're going to have self.top be equal to new node, like this. And then the other possibility is that we have a stack that has items in it. So we'll say else, and we'll bring this up like this, and we're going to push that 11 onto that existing stack. So we'll say new node.next equals self.top. So that is new node.next is going to point to the same node that top is pointing to, like this. Then we'll say self.top equals new node. That moves top up and adds that into our stack. So let's add this in with the rest of our code like this. And the only thing left to do is to increase the height by 1. So we'll look at this code in a moment in VS Code, and we'll create this stack with one item on it. And then we will push the number 1 onto that, and we'll print this out, and we should get 1 and 2. All right, so let's flip over to VS Code. There's our push method there. This is where we create our new stack, and we create it with a node with a value of 2. We already know that this works because this is what we did in the last video. What we're going to test in this video is this line of code here. Does this push method work? And we'll know that that works by running the print stack method down here. All right, so I'm going to run this, and that prints out 1 and 2. All right, so it looks like we have a working method for push. Now let's do our pop method. Let's bring up our stack like this. Pop is going to be the removal of that top node, and then you have the top pointer point at the next node down. And then, of course, we're going to return that node that we popped from the stack. And then we also have to code for this situation where we don't have any items in the stack. So if you're going to code this, go ahead and pause it here. Otherwise, I will get into the code. So we'll start this off like this. We'll say pop. We don't pass it any arguments. And we'll code for this situation where we have an empty stack first. We'll say if the height is 0, we'll return none. Otherwise, we do have items in the stack like this, and we want to return that top node. So we're going to need a variable to point to it. So we'll say temp equals self.top, like that. Once we've done that, we can move top down to the next node. So we'll say top equals top.next, and that moves that down. So now we need to remove that node from the stack. So we'll say temp.next equals none. That is temp.next equals none. and that removes that from the stack. Now let's look at this in with the rest of our code, like this, and the only things left to do are to decrement the length by 1, and then we'll return temp, and that is our pop method. So we'll look at this code in a moment in VS Code, and when we do, we will build this stack. We'll print this out to make sure it's printing out correctly. Then we'll pop this item off here, take a look at that item that we popped off, and then we'll print out the linked list with the items remaining, and we should have 3, 23, and 7. Okay, so let's flip over to VS Code. So there is our pop method there, and this builds the stack that we just looked at, and then we're going to start off by printing it out with this line here, print stack, and I'll run this, and that prints out our stack 11, 3, 23, and 7. And then what I'm going to do is, in between where we created our stack and where we printed our stack, I'm going to insert this line of code. So we're going to print my stack.pop here, and then we have a line break after it. And then down here, we're going to print out the items that are left on the stack after we have popped that item off. And I'm going to run that. So this is the node that we popped off, and the stack now has 3, 23, and 7. And to take a look at what's in that node, I'm going to come up here. I'm going to type temp.value, and now I'll run it again. And now you can see that the node that we popped from the stack is the 11 node. So of course, I'll come back up here and remove the .value here. So we're just returning temp, so we return the entire node. All right, and that is our method for pop. Now let's look at queues. And queues are something we're all familiar with. We join a queue whenever we get in line. And then there's other people that can get in line behind us. But if you were there first, you will be the first person out of the line. This is called FIFO, first in, first out. And when we add people to the queue, like this, we use the term in queue. When we remove people from the queue, like this, we use the term dequeue. Now let's look at a couple of data structures that we could potentially use to create a queue. Let's start with a list. So for something to be a queue, you add on one end and you remove on the other end. With a list, removing and adding from the end is O of 1. But on the other end, removing and adding is O of n. So if you have a queue, let's say we're going to add on this end and we're going to remove on this end, we have one way that is O of n and the other way that is O of 1. Likewise, if we add on this end and remove on this end, we still have one end that's O of n and one end that is O of 1. Now let's compare this to a linked list. With a linked list, removing is O of n on the end, but adding it back on is O of 1. On the other end, removing is O of 1, and adding it back on is also O of 1. So you have 3 O of 1s here and 1 O of n. And that means what you don't want to do is you don't want to dequeue from this end. You want to enqueue from this end and dequeue from this end because both of those are O of 1. With a linked list, we call these head and tail. A change that we're going to have for it to be a queue is we're just going to call these first and last. And that is our intro to queues. All right, now let's build our queue constructor. So we're going to build one of these, but we're going to represent it like this. And in order to build this, the first thing we have to build is a node, which really looks like this, and the constructor looks like this. So this is the same node constructor that we used with linked lists, and the same one we used for stacks. Now let's start off our queue class and start building the constructor. So the first thing we're going to do in the constructor is build a node like this. We'll pass that a value, and that creates our node. And then we'll say first and last are equal to the new node, like that. And the length is going to be 1. And that is all of the code for our constructor for our queue. In order to create a new queue, we would do something like this. My queue equals queue. We pass it the number 4. When we do this, it creates all of this. It not only creates the node, it creates first and last and a length of 1. So now let's go look at our constructors for the node and for creating a new queue in VS Code. So there's the node class here. Then I'm going to scroll up so we can zoom in. And this is where we create our queue class. And this is the constructor for the queue class that we just built. Then down here we have a print queue method. So we can see the contents of the queue. And this is where we create our new queue. We'll start this with the number 4. And then we'll use that print queue method down here to print that out. And we should get the number 4. Okay, so I'm going to run this. And that returns the number 4. All right, that is our queue constructor. So now let's build our enqueue method. And enqueue is just getting in line. So the way we're going to do enqueue is going to look like this. And that will add that onto the end of our queue. So this is one of our possible scenarios for adding an item into the queue. The other one is if we have an empty queue. In this case, we'll have first and last point to that new node. So if you're going to code this, go ahead and pause it here. Otherwise, I will get into the code. So we'll say enqueue, we'll pass it a value. We'll use that value to create a node like that. So the first scenario we'll code for is if we have an empty queue where we're going to have first and last point to that node. In other words, it is the first and last item in line. So to do this, we have to test to see if the queue is empty. And we'll do that by saying if first is none, we'll have first be set equal to the new node like that. And we'll also have last set equal to the new node like that. So let's add this in with the rest of our code. So that is for if we have no items on the list. If we already have items on the list, we'll say else. Let's build out this else statement. So we'll say last.next equals new node. That is last.next equals new node. Then we'll say last equals new node, and we'll move that over, and that adds that. onto the end of our queue. So let's add this code in with the rest of our code like that. And the only thing left to do is to increase the length by 1. So we'll look at this code in a moment in VS Code. And when we do, we'll build this queue where the first node has a value of 1. And then we'll run in queue to add a second node with a value of 2. And then we'll print this out and we should get 1 and 2. All right, let's flip over to VS Code. Okay, there's our in-queue method there. And this is where we build that new queue that starts out with a node with the value of 1. And this is where we will in-queue a second node with the value of 2. Down here is where we will print that out, and we'll expect to see 1 and 2. All right, so I'll run this, and that has returned 1 and 2. All right, that is our method for in-queue. Now let's create our dequeue method. Dequeue is going to look like this, and then we're going to return that node that we removed. But we have a couple of edge cases. One is if we only have one item in the queue, and the other is if we don't have any items in the queue. So we'll start with this scenario first, and we'll say dequeue. We'll say if the length is 0, we will return none. And we'll remove that. And let's do this for one node. So it doesn't matter if we have one or if we have two or more. That means we're going to return a node. So we need to have a variable point to it. So we'll say temp equals self.first. And for removing one item, we'll say if the length is 1, we set first and last equal to none, just like that. So let's look at this in with the rest of our code. So far we have written code for if we have 0 items in our queue, and if we have 1 item. So now we're going to do this for 2 or more items. So let's focus in on the else, and we'll bring this up. And remember, temp is already pointing to self.first. We already did that. So the first thing we're going to do is move that first pointer over 1. So we'll say first equals first dot next. We'll do that with this line of code here. First equals first dot next, and that is going to move that over. Then we'll say temp dot next is none, and we'll do that with this line of code here. Temp dot next equals none, and that removes that from our queue. So let's look at this with the rest of our code. And the only things left to do are to decrement the length by 1 and return temp. So we'll look at this code in a moment in VS Code, and we'll build this queue with a 2 and a 1. And that way we can test all 3 of our scenarios. First, we'll test to see if this works with 2 or more items, and we'll dequeue that. Then we'll see if it works with 1 item, and we'll dequeue that. And then we'll run it again with 0 items to make sure that works and returns none. All right, now let's flip over to VS Code. Okay, so there is our dequeue method there. And this is going to build our queue with 1 and 2. And then we'll run this line of code to print out the queue, and we should get 1 and 2. So I'll run this. Okay, so there's our 1 and our 2. And then what I'm going to do is I'm going to scroll up here, and then I'm going to replace this print queue with this. And all we're doing here is running dequeue 3 times. Once for when we have 2 items in the queue, and then for 1 item, and then for 0 items. So I'll run this, and that gives us our 2 nodes, and then it finally returns none when we have the empty queue. And then to make sure that these nodes that are being returned are the values that we're expecting, I'm going to come up here. Then I'm going to change this to temp.value, and then I'll run this again. And that is returning the 1 node and the 2 node, and then finally returns none. Then I'll come up here and remove the .value. And it looks like we have a working method for dequeue. Welcome to trees. And we have already seen a tree in this course. It's a linked list. So a linked list is just a tree that doesn't fork, but it is actually a form of a tree. So we'll use this as the starting point for creating the tree for this section. Remember, this node looked like this. So I'm going to put this back, and then we'll turn this into a node for a binary tree. So the first thing I like to do when we move to a new section for each data structure is have a different color. So a binary tree is going to have 2 arrows like this, and it's going to look like this: value, left, and right. So let's move this back, and let's build out a small tree. So this node, of course, can point to other nodes. So if you have something like this, you can think about it as dictionaries like this. That's essentially the same thing, except this is a lot easier to look at. So the way we've designed our nodes with value, left, and right, they're set up where they can only point at 2 other nodes. So if you set it up that way, it's going to be a binary tree. But trees don't have to be binary. You could have this point to 3 nodes or 100 nodes, or have it where you could point it to unlimited nodes. But for what we're going to build, each node can only point to 2 other nodes. And then, of course, these new nodes that we've added can also point to 2 other nodes themselves. So now let's look at some terminology. This tree here is what is called full. In a full tree, every node either points to 0 nodes or 2 nodes. So if you do something like this, now you have a node, the 7 node, that only points to 1 node, so it is no longer full. So let's remove that, make it full again. And if we remove these 2, it is still full, but it is also something else. It is perfect. With a perfect tree, any level in the tree that has any nodes is completely filled all the way across. So this is also a perfect tree. But if we remove these 2, it is no longer perfect, but it is still full. So let's bring these 2 back. So a perfect tree is also something else. it is complete. So with a complete tree, you are filling the tree from left to right with no gaps. So if we add a node down here, it is still complete because we are filling the tree from left to right. But it is no longer full, and it is no longer perfect. If we add one more node like this, filling this from left to right, it remains complete, but it is now also full. But it is not perfect because we haven't filled it all the way across. So if we do this, now it is full and perfect and complete. Okay, so let's focus in on this tree and drop some of these off. So this node here is a parent of these two child nodes. These two child nodes, because they share the same parent, are also called siblings. And every node can only have one parent. So if you see something like this, where a node has more than one parent, then it is not a tree. So let's put this back. And child nodes, of course, can also be parent nodes. Now these nodes at the bottom, they don't have any children, and a node that doesn't have children is called a leaf. All right, that is our intro for trees. So the binary tree we looked at in the last video was a binary tree, but it wasn't a binary search tree. In order for it to be a binary search tree, the nodes have to be laid out in a particular way. So let's take a look at that. So let's say we have one node in our tree, and we're going to add another node. With a binary search tree, if the number is greater than, it's going to go on the right of that node, and if it's less than, it's going to go on the left of that node. And because 76 is greater than, we're going to place it there. Now let's take a look at another node. The 52 is greater than 47, and we're always going to start by comparing it to the node at the top. And because it's greater than, we're going to go to the right, but there's already a node there. So what we're going to do is we're going to compare that 52 to the 76, and because it's less than 76, that goes on the left of that node. So let's look at another node, a 21. We're always going to start at the top, and because the spot to the left of the 47 is open, we'll place it right there. So let's just look at a few more here. We'll say 82. We'll start at the 47. It's greater than. We'll go to the right. We'll compare it to the 76. It's greater than again. In this case, that spot is open, so we'll place it. 18. It is less than 47, so we go to the left, and we look at the 21. It's less than the 21. That spot's open, so we'll place that there. And one final node. We'll start at the 47. It's less than. We go left to the 21. 27 is greater than the 21, so we place that on the right. So a couple of things to point out about a binary search tree. If you take any node in the binary search tree, all nodes below it to the right are going to be greater than that node. Everything on the left is going to be less than. And that is our overview of binary search trees. So now we're going to look at binary search tree, big O. In order to do this, we'll have to do some simple math. So the number of nodes in this tree right now, obviously, is 1, but you can also write this as 2 to the 1 minus 1. 2 to the 1 is 2, minus 1 equals 1. And you'll see why I'm doing this here in a second. But if we have a second level like this, this is 2 to the 2 minus 1. 2 to the 2 is 4, minus 1 is 3. 2 to the 3 minus 1, 2 to the 4 minus 1. Now, as we get into very large numbers here, that 1 is insignificant. So let's remove this, and we'll say this is approximately 2 to the 4 nodes. This is approximately 2 to the 3, and 2 to the 2, and 2 to the 1. Now, if you're going to look for a node in this tree, it's going to take one step, obviously. But when we go to 2 levels, let's say we're going to look for the number 76, that is 2 steps. So we have 2 to the 2 nodes, approximately, and it took us 2 steps to find something. Let's say we're going to look for the number 27. It is 1, 2, 3 steps. And if we were going to look for the number 49, in this case, it would be 1, 2, 3, 4 steps. We have 2 to the 4 nodes, and it took 4 steps. So it's 4 steps to find something. It's 4 steps to remove something because you have to iterate through the list, find a node, and then remove it. And it's also 4 steps if we're going to add a node. If we're going to add a node under that 49, we would have to iterate through 4 steps, and then we could insert it. So that means that all of these are O of log n. And O of log n is very efficient. So remember, O of log n is achieved by doing divide and conquer. So let's bring our tree back here and show how it is that we're doing that. So if we're going to look for that 49 node again, we start at the top, and then we go right. And when we do, we just made it where we never have to look at anything that's on the left of the 47. So we are effectively removing these from the search. And that's not a big deal when you have a small tree like this, but if you had 1 million items in the tree, you just made it where there are 500,000 items that you don't have to look at. And then from here, we're going to go left, and now we have made it where half of the remaining nodes don't need to be looked at, like that. And then we finally come down to the 49 node, and we have done that again. And that is divide and conquer. So let's bring all of this back. So for our examples for calculating time complexity so far, we have used a perfect tree. And a perfect tree is going to give you your best possible scenario. And remember, we measured best possible scenario with omega. You're more likely to see a tree that looks like this. But even in this situation, you would say that this is roughly log n. But now let's look at our worst case. Our worst case would be if we had a node, and then the next one was greater than, and it goes to the right, and the next one is greater than that, and it goes to the right of that one, and the next one is greater than that, and it just keeps going on and on in a straight line. If the tree never forks, it is essentially a linked list. So let's say we want to go look for the 91 node. How many steps would it take? It would be 1, 2, 3, 4, and we have 4 nodes in the tree. That is O of n. So the big O of a binary search tree technically is O of n, not O of log n. So let's bring our other nodes up here like this. What we assume with a binary search tree is it's not going to be a straight line. We're not going to have that worst possible scenario, and we treat it as if it is O of log n. We don't treat this like an O of n data structure. So for lookup, insert, and remove, we treat this as if it is O of log n. Now let's compare this to a linked list for lookup, insert, and remove. So if we're going to do lookup with a linked list, say we're going to look for the number 91. We start at the beginning, and we iterate through the list until we get to the number 91, and because we have to iterate through, this is O of n. So a binary search tree is better than a linked list in this situation. How about if we're going to remove an item, and we're going to remove it by value? Once again, if we use the 91 as our example, we're going to iterate through the list, get to the 91, we're going to remove that. That's O of n because we had to iterate through the list. Also, in this situation, a binary search tree is better. Now let's look at insert. Our linked list here is sorted, but there is zero advantage in a linked list to sorting your data. So if you're going to insert a node, you would just append it to the end, and that is O of 1. So I want to point this out because if you get a question, say in an interview, and they say, we need to be able to add data to a data structure very quickly, but retrieval speed is not very important because we're not going to go retrieve things very often. But we could have bursts of data coming in, and we want to make sure nothing gets dropped, so we want this to be able to be added as quickly as possible. If you were going to choose between a binary search tree and a linked list, which one would you choose? Well, the linked list is better for that situation. There is no data structure that is the best answer in all situations. That's why it's important to understand the big O of all of the operations that you would do with a particular data structure. So let's look at all three of these side by side between linked lists and binary search trees. So insert is faster for a linked list because we can just add an item onto the list and it's O of 1. But lookup is O of log n for a binary search tree, and the same is true for remove. And if you look at lists and you compare them to binary search trees, all of that is the same. Inserting an item, you can just put it on the end, O of 1, but lookup and remove by value will be O of n. Now, if you're looking up by index, obviously that's very fast. But if you're looking up a value or removing a value, you have to iterate through the list. And that is our overview of binary search tree, big O. Now let's build our binary search tree constructor. The first thing we'll need to do is build a node. And remember, this node is going to look something like this. So the constructor is going to look like this. Value, left, and right. And once we have this, we can start building our binary search tree. We'll start the constructor out like this. And I'm just going to focus in just on the constructor like this. We pass it a value, and we use that to create a node like that. So to explain what we're going to do in the next line of code here, I'm going to make this part of a tree like this. Each node needs to have something pointing to it. And every node in this tree has something pointing to it, except that first node. So we saw this concept with linked lists. If you're going to have a linked list, you have to have something pointing to the first node, because that's the only way you have a way of getting to that node. So in a tree, we have something similar. We don't call it head, we call it root. So we have to create this root variable. So we're going to say self.root equals new node. And we're not going to keep track of the length in a tree. So this is a working binary search tree constructor. But I want to teach a different concept here. So I'm going to remove the code here. And we're making the assumption when we build this binary search tree that we're going to create this with the first node at the time that we build the tree. And you don't have to do it that way. We've done it that way on all of the data structures so far. But you could just create this where root is equal to none. You create an empty tree. And when you add the first item, you add it with the insert method. You don't add it at the time that you create the tree or the linked list or whatever you're building. So what I'm going to do is I'm going to bring this code back and change it where it creates an empty tree at the time that we run the constructor. So I'll go through this line by line. So in the first line, we passed this a value. The only reason we did that was to create that first node. So now we can remove that. The second line, all this does is create a node, so we can remove that. So this last line, self.root equals new node, we're going to change that to be equal to none. Now that becomes our entire constructor for initializing a binary search tree. Now let's bring back where it said class binary search tree, and let's go look at this in VS Code. So there's our class for our node there, and that has value left and right. And this is our class for our binary search tree. And then for our binary search tree, that is the entire constructor there. Then we're going to create a new binary search tree called myTree. And then down here, we'll just print out myTree.root. And it should return none, because up here we said that self.root was going to be equal to none. Okay, so I'm going to run this, and that returns none. All right, that is our binary search tree constructor. In this video, we're going to walk through the steps to create the insert method. Then in the next video, we'll take those steps and walk through them and actually create the code. So I'm going to bring up our binary search tree like this, and we're going to insert this node. And obviously that's going to fit right there. But let's walk through the steps that you would have to go through to be able to write the code to figure out that it does go there. So the first step would be to create a new node. So what I'm trying to do in this video is go through the steps that you would go through if you took out a piece of paper and said, okay, I'm going to figure out all of the steps to insert a node into a binary search tree. So the left is essentially our piece of paper that we're taking notes on. So in order to have more room for that, I'm going to move our tree over like this. And now the next step, we need to compare that new node with a value of 27 to this node here. And if the node we're adding is less than, we're going to go left. And if it's greater than, we're going to go right. So let's add this to our notes over here. If it's less than, we're going to go left, else it's greater than, and we're going to go right. And obviously in this case, we're going to go to the left. And when we do, there are two possibilities. Either there is a node in that spot to the left, like we have here, or there isn't. And if there isn't, we can just insert it right there. So if to the left of the 47 is equal to none, we'll insert it. But if it isn't, then we need to come down here and do the whole process again. So we could say if the direction we're going is none, then we'll insert the new node, else we'll move to the next node. So now we're going to compare our new node to this node, the 21 node. So we're going to do this again. If it's less than, we go left, else it's greater than, and we go right. So in this case, that's going to be to the right. And when we go to the right, we have to determine, is that spot empty? Is 21 right equal to none? If it is, we're going to insert it, and in this case, it is. So the thing that should jump out at you is that we did these two lines of code for this node, and then we did it for this node. So that is an indication that these two lines of code should be inside of a loop. And because we don't know how many times we're going to be iterating through the tree, this cannot be a for loop. It has to be a while loop. Now, as we were iterating through this tree, we had this arrow that was pointing at the node that we would compare the new node to. So we need to name this arrow. We're going to call this temp, and then it will move through the tree, and we will compare new node to temp. So I'll bring this up here. We need to have this start at the top of the tree. So we'll set it equal to root. And we need to declare this variable before we ever get into that while loop. So we'll need to put this above that. So these steps right here cover most of our situations. But we do have a couple of edge cases. The first one being if we have an empty tree. If this happens, we'll just set root equal to the new node like this. And in this situation, we don't need to go through the while loop. We don't even need the temp variable. So we can put this above the temp variable like this. If root equals none, then we'll set root equal to the new node. So let's bring our tree back like this. And we do have one other edge case. And to show this, I'm going to replace our 27 node with a 76. So if we're going to insert this, we'll start at the 47 and then we go right. And now we have a problem. You can't have this be equal to a node that we already have in the tree. All of our code that we've written is less than go left and greater than go right. There is nothing in there for equal to. You cannot have duplicates. The new node that we're inserting needs to be compared to each node as we're moving through the tree. So this has to go inside of our while loop. If the new node is ever equal to temp, in other words, the next node that we're comparing it to, at any time, we're going to return false. And that is the last step that we need to write down. So what we're going to do is we're going to pick up right here in the next video, and we're going to use these steps to code our insert method. But for now, those are the steps for insert. Okay, so now let's code our insert method. And as I mentioned at the end of the last video, we're going to start right where we left off with the other video with all of these notes. I'm just going to bring these down here to the bottom, and we'll start coding this. So we're going to say insert, we're going to pass it a value, and then we'll come down here to the notes. The first thing is to create a node. So we'll do that like that. That creates our node, and we can remove that from our list. The next item on the list is if the root is equal to none, then we're going to set root equal to new node. That is this situation here where root is equal to none. We have an empty tree, and we're going to set root equal to the new node. We'll do that like this. If root is none, root is equal to the new node. But there's one other line of code that we need here. We need a return statement, because if we're going to insert this directly into our tree at the root, we don't want to continue running code in this method. So now we can remove that. Then we're going to say temp equals self.root. That's actually the way we would write the code to declare that variable. So we can just move that up. So that brings us to our while loop. So our while loop is going to be while true. And normally you run a while loop until this condition is false, and obviously true is always going to be true. But the way we're going to break out of the while loop is by hitting a return statement at some point within the loop. So remove that. Then we'll say if new node equals temp, return false. And that is this situation where the new node is equal to another node in the tree. And if this happens at any point, we need to return false. So we'll do that like this. If new node.value, and it's important that you not just say if new node equals temp, you have to say new node.value and temp.value because we're comparing the values. If they are ever equal while we're running through the while loop, we're going to return false. So now we can remove this. Now we're going to say if it's less than, we're going to go left, else the number is greater than, and we're going to go right. So we're going to start with left, and we'll say if new node.value is less than temp.value. And since we're running out of space here, I'm going to move this if statement up to the top of the screen. But I want you to notice that this is inside of our while loop. So everything we're going to do to code out the rest of this method is going to be contained in that while loop. So we're going to move this up like this. And the second if statement in the notes down here is actually nested inside of the other if statement. And we'll see that in a second. But for now, I'm going to remove the notes, and it's going to be easier to finish explaining this by bringing up a diagram. So we're going to insert this node here. And remember, temp is going to be pointing at the root here. So this if statement at the top, we're saying if new node.value is less than temp.value, and in this case it is. So that means we know we're going to go left, but there are two ways we can go left. Either that spot is open like this, in which case we're going to place that node. Otherwise, there will be items here, and then we'll need to compare the 18 to the next item in the tree. So let's assume that this spot is open first, and we'll say if temp.left is none, which means that spot is open, we're going to set temp.left to be equal to the new node. Now that we've placed that, there's one more step that we need to do here, and we need a return statement. So we'll return true. So that's what we do if that spot is open. If the spot is not open like this, we need to move the temp variable down to point at that 21. So we'll say temp equals temp.left, and it moves temp down. And remember, this is all inside of this while loop, so now we're going to run through all of this again. So obviously we're going to go left because the 18 is less than the 21. So then we come to this line. If temp.left is none, and in this case it is none, then we're going to set temp.left equal to the new node like that. And then of course we'll return true, and we're done placing that node. Now let's look at inserting something on the right. I'm going to bring our temp variable back up here. I'm going to move this to the left since we're going to be inserting on the right. We'll need a little bit more room. So for this, we're going to say else. And I'm going to remove that 82 node on the lower right-hand corner of our tree there. That'll be the one we're going to insert. And just like on the other side, we can have a situation where we have a node to the right of the 47, or that spot can be empty. If that spot is empty, we'll say if temp.right is none, and in this case temp.right is none, then temp.right equals new node. That is temp.right equals new node. And then we need to return true. The other option is that there is an item there, and then we'll say temp equals temp.right. That is temp.right. That moves temp down. And remember, this is in a while loop, so that causes us to go through all of this again. So then we'll say if temp.right is none, and in this case it is none, then we'll place that temp.right equals new node. That is temp.right equals new node. And that is everything we need to do to be able to insert that node. So now let's look at this code in with the rest of the code that was in the while loop. That is our full while loop there. So to walk through this, this is for the situation when we try to place a node that is a value that is already in the tree, like this, an identical value. Then if it's less than, we go left. If it's greater than, we go right. Now let's look at this while loop in with the rest of our code, like that. And that is the entire insert method. And we'll look at this in a moment in VS Code. And when we do, we're going to create a tree that starts with a number 2, and then we're going to add a number 1, and then we're going to add a number 3. And to make sure that these are being inserted correctly, we'll print out root.value. And then if we do root.left.value, we should get 1, and then root.right.value, we should get 3. So let's flip over and take a look at this in VS Code. Okay, so there is our insert method. I'm going to scroll up. This creates our binary search tree here, and we're calling it myTree. Then we're going to say myTree.insert. That's going to put the number 2 in at the root. And then we're going to insert the number 1. That should go on the left. And then insert a number 3. That should go on the right. And then down here, we have 3 print statements to make sure that the tree was created correctly. So we're going to print myTree.root.value. That should return the number 2. And then we have myTree.root.left.value should return the number 1. And then print myTree.root.right.value. And that should return the number 3. All right, so I'm going to run this. And that has returned 2, 1, 3. All right, that is our method for insert. So now we're going to write our contains method. So for contains, we're just going to see if a tree contains a particular value. So if we were looking for the number 27, that is in the tree, we would return true. If we were looking for the number 17, that is not in the tree, we would return false. So just like we did for insert, I'm going to walk through all of the steps for the contains method, and then we will go through the code. So the first thing we've done in all of our data structures to this point is to code for a situation where that data structure is empty. So we'll say if root equals none, we'll return false. And we'll talk more about this scenario at the end of the video. But let's bring our tree back like this. So the next step is we'll need a variable that we'll use to traverse through the tree. We'll call that temp. So let's say we're looking for the number 27. It's less than 47, so we go left. It's greater than 21, so we go right. And now it is equal to. That means we've found the value. So let's bring this up to the top here and actually create that variable. We'll say temp equals self.root. So now let's look at what happens if we're looking for a number that is not in the tree, like the number 17. We're going to go to the left. 17 is less than 21, left again. It is less than 18, we go left again. If we ever get to a point where temp is equal to none, that means the number we're looking for is not in the tree. And it also means we should stop iterating through the tree. So our while loop is going to say, while temp is not none, we'll continue doing this while loop. If we ever hit none, that will break us out of the while loop. Inside the while loop, we have 3 scenarios. Either the number that we're looking for is less than temp, in which case we're going to go left, or it's greater than, we'll say else if it's greater than, we'll go right. And then our third scenario is that it is equal to. So whenever the value that we're looking for is equal to temp, we'll return true because that means that value is in the tree. If we ever hit none, that means that number is not in the tree. It'll break us out of our while loop, and we will return false. Okay, so those are all of our steps for the contains method. Let's move those steps down to the bottom here and write the code. So we'll say contains, we'll pass it a value, the value that we're looking for. And now let's start working through our list. If root is equal to none, we're going to return false. So that is this situation where we have an empty tree. So we're going to say, if root is none, we return false. And we'll remove that from the list. Next, we'll create our variable temp equals self.root. And that's exactly the way we would write the code. So we can just move that up. Then we'll create our while loop. And this is actually the way we would write the code. While temp is not none, we'll just move that up. And inside of that while loop, if it's less than, we go left. We'll write that code like this. So let's walk through this. We're saying if value, the value that we're looking for, is less than temp.value, in this case, that's 47. Let's say we're looking for 27. That would be less than. We would say temp equals temp.left, and that moves that down. So let's remove this tree, and we can remove that item from our list. Then we'll say else if it is greater, we'll go right, like this. This is saying if the value we're looking for, say that's the number 82, if it is greater than temp.value, in this case 47, we're going to say temp equals temp.right, and that moves temp down. So let's remove that, and then we can remove that item from our list. And then finally, we're going to say else it must be equal, and we're going to return true. And then we'll just do this because that is the only option that we have left if that item is in the tree. So we'll remove that. Then there's also the possibility that that item is not in the tree. That'll break us out of the while loop, and then we will return false. Now let's zoom in on this while loop and just walk through a couple of scenarios how this code would run. I'm going to bring a tree up here, and for this first one, we're going to look for the number 27. So we're going to say while temp is not none, which is to say while it's still pointing to a node, this will run. If value is less than temp.value, and it is, 27 is less than, we're going to say temp equals temp.left and move this down. Then we'll run the while loop again. If it's greater than, we're going to move right, and it is greater than. And then we'll run the while loop again, and this time, that is the value we're looking for, and we're going to return true. Let's bring this up here and look for a scenario where we don't have that item in the tree. We'll look for the number 17. So we'll say while temp is not none, we're going to go left. runs the while loop again, and we're going to go left again. We run the while loop again, and now it's less than again, and temp.left equals none. Now when we run the while loop, temp is equal to none. It breaks us out of the while loop, and we return false. So let's drop this tree out of here, and we'll bring in the rest of our code. Now that we have all of this done, I want to circle back to these two lines of code. And the reason is, you don't actually need them in this code. The reason I left these in here is while you're going through all of these steps, if you're writing this out on a piece of paper, it's very common to say, okay, first thing I'm going to do is, if the tree is empty, I'm going to return false. And if you put this into your code, everything works just fine. If you look at different solutions for the contains method online, it's very common to see code that has the equivalent of these two lines in there. And you can see why. Whoever created that code went through the steps on a piece of paper, they wrote this out, they put this in their code, and it works. So I'm going to remove this, and we'll walk through a situation where we have an empty tree. We're going to set temp equal to self.root. That's just going to make temp equal to none. We move down to our while loop, which says, well, temp is not none. Well, temp is none, so we're going to skip that, and we're going to return false. So that is the final version of our code for contains. So this is what we're going to look at in a moment in VS Code. We're going to build this tree, and just like we've been doing throughout the video, we will first look for the number 27, and we would expect that to return true, and then we'll look for the number 17, and we'll expect that to return false. All right, so let's flip over to VS Code. Okay, there is our contains method, and then down here, this creates our tree and puts all of the items that we had in the diagram in there, and then I'm just going to scroll this up, and this is where we look for the number 27 that is in the tree. You can see that right here. And then down here, we look for the number 17, which is not in the tree. Okay, so I'm going to run this, and you can see the first one is true, and the second one is false. All right, and that is our method for contains. So with this method, we are going to find and return the node with the minimum value in a tree. So I'm going to bring our tree up like this. So if we start with the 47 node there, the node with the minimum value below that node, you can look at that and see it's the 18. But the way we're going to find that is we're going to go to the left, and we go to the left again, and then we look to the left one more time, and if that is equal to none, we'll know that that 18 is the node with the minimum value, and then we'll return that node. But we're going to write this method where we can find the minimum value node in any subtree. So for example, we can start with the 76 node, and we will only be looking at nodes in the subtree that are below the 76 node. And we'll do the same process here, where we go to the left, and then we'll go to the left again, and if this is equal to none, we'll know that the 52 node is the node with the minimum value in that subtree. So I'm going to shrink this down into the corner, and then we'll start writing our code. So we'll call this min value node, and then we pass it a node. We'll call that current node. I will just call that variable current here, but I like to call it current node as the variable name because it is self-documenting. You can see that you need to pass this a node. Then we'll start our while loop. So we'll say, while current node dot left is not none. So current node dot left, in this case, is not none because there is a node there. And then we'll say current node equals current node dot left, and that moves that pointer down. So then we'll run the while loop again, while current node dot left is not none. Then we'll make current node equal to current node dot left, and then we'll run the while loop one more time. Current node dot left in this case is none. It breaks us out of the while loop, and then we return current node. So now let's look at doing this on this subtree here. It works the same way on a subtree. We'll run the while loop, and we'll say, while current node dot left is not none, we'll set current node to be equal to current node dot left, and then when we run this again, current node dot left is none. It breaks us out, and then we'll return that 52 node. So we'll drop this tree out here. That is all of our code for the min value node method. We'll look at this in a moment in VS Code, and when we do, we'll run it with this line of code, where we pass this the root node, like this. We'll expect that to return that 18 node, and then we'll do it again for this subtree, and we'll do that with this line of code. We'll say mytree.root.write, and that will pass it the 76 node, and we'll expect that to return the 52 node. So now let's flip over to VS Code and take a look at this. So there's our min value node method there, and then these lines of code here will create that tree that we just saw, and this is where we run min value node with the root and run it with root.write. So I'll run this, and you can see it returns 2 nodes. We want to make sure it's returning the correct 2 nodes. So I'm going to come up here to our method and have it return dot value, and I'll run this again. And you can see here that this returns the 18 and 52 nodes, which was exactly what we were expecting. And then remember, we have to come back up here and remove the dot value to make sure that it's returning the entire node and not just the value from the node. So I'll delete that. And it looks like we have a working method to find the node with the minimum value. Now let's look at hash tables. So to explain this, I'm going to bring up an address space here, addressed 0 through 7. And for our implementation, this is actually going to be a list. So to demonstrate the hash table, I'm going to create a store, a hardware store, and we're going to have items and then the number of those items. So we'll have nails and nuts and bolts and things like that. So I'm going to first start by talking about the built-in hash table, which is dictionaries. So dictionaries are made up of a key value pair. So nails is the key and 1,000 is the value. So the way a hash table works is this. We're going to need a hash function or a hash method. And what we're going to do is perform a hash on the key. So we take that key, run it through the hash, and in addition to getting our key value pair back, we get an address. So we ran nails through a mathematical function and it returned the number 2. So that's going to be the address where we store that key value pair. And that is how a dictionary is stored. So now let's talk a little bit about the hash itself. There are two characteristics about it that are important. The first is that it is one way. So if we take nails, we run it through the hash, and we get the number 2, the thing that we cannot do is take the 2, put it through the hash, and have it produce nails. It is one way only. The other thing about a hash is that it is deterministic. And deterministic means that for a particular hash function, every time we put nails in, we expect to get the number 2 every time. That means it is deterministic. So this hash is going to embody these two characteristics. So even though Python includes a hash table, which is dictionaries, we're going to build our own. We'll create our own address space by creating a list, and then we'll create methods. So in this case, to set an item, we're going to have a key and a value. And to use the same key value pairs we did before, we'll say nails with a quantity of 1,000. We will create our own hash that we'll use to hash the key, and our key value pair is going to be a list, and the hash is going to produce an address. So at this address in our list, we will put this other list with nails and the quantity of 1,000 in that spot. So that will create a list within a list. And let's set another item here. We'll say screws. We'll run this, and we're going to get our key value pair and an address, and we'll store that. And let's say nuts with 1,200, and we're going to say that's at the address of 2. But we do have a problem here because we already have a key value pair at that address. We don't want to just overwrite that and replace it. So let's bring this back. We'll talk about how we're going to do this in an upcoming video, but we will be able to store both of these at this address. And let's just add one more here, bolts, with a quantity of 1,400. We get an address, and we store that there. So now that we have these in place, we can do something like get items bolts, and we can run the hash on bolts. And because the hash is deterministic, we know the address where it is stored. We can go directly to this address and get the quantity of bolts. So let's put that back, and we'll run get item on nails. Same thing. Deterministic means that we know the address, and we come up here. And this one is a little bit more complicated. We have multiple key value pairs at that address. So we know we're going to have to create some kind of loop to go through those to get to the quantity. And that is our quick overview of hash tables. So now let's talk about collisions. So let's bring up an address space here and bring in some key value pairs like this. So a collision happens when you put a key value pair at an address where there was already a key value pair. So in the last video, we talked about how is it that we have a second key value pair go in at this address without overwriting the last one. And the way we're going to do that is both of these key value pairs exist within another list at that address of 2. But for the sake of keeping this a little cleaner, I'm just putting them in here like this. So this technique of dealing with collisions where you just put them at the same address is called separate chaining. So in another popular way of dealing with collisions, if we already have a key value pair at the address that this maps to, what you do is you go down until you find an empty address and you put the key value pair there. And then if you have another one, you're going to keep going until you find an empty spot like this and then store this. This is called linear probing, and that is a form of open addressing. And there are a lot of ways to do this with open addressing. Linear probing is just one of them, but this makes it where you don't have more than one key value pair at any address. So separate chaining is what we're going to do in this course. So I'm going to take these, I'm going to move them up, and this is what it's going to look like when we do this. Now another way of doing separate chaining, let's remove these, is instead of having lists that are all stored at that address in our list, is we can have linked lists at those addresses like this, and then say you're going to look for paint, you go to the address of 2, and then you would iterate through the linked list until you find it. But I'm going to bring these back since this is the way we're going to do it, and that is a few different ways of dealing with collisions. So now let's build our hash table constructor. Let's bring up our address space here. So one of the points I want to make about a hash table is that you should always have a prime number of addresses. We've been doing this 0 through 7, but I want to make the point that a better address scheme would be to remove that last 1 and just use 0 through 6. And the reason for that is a prime number increases the amount of randomness for how the key value pairs are going to be distributed through the hash table. So it reduces your collisions. So now let's build the constructor. We're going to say class hash table, and the constructor, the only thing it's going to do is build this list 0 through 6. So we'll do that like this. So the only argument that will pass this is the size. And if you haven't seen this before, where you set a parameter equal to something, this just becomes the default if you don't pass it an argument. So our default size is going to be 7. Then we're going to call this list data map. We set it equal to none and then times the size. So it's going to create a list with 7 items in it, and all of those are just going to contain none. So in addition to creating this constructor, I also want to create our hash method. So I'm just going to bring in all of the code for that at once, like this. Remember, the hash is what we pass the key to determine the address where we store that key value pair. So let's walk through how I created my hash method here. We're going to have a variable, my hash. We're going to initialize it to 0. Then we'll loop through the letters in the key that we passed the hash method. And when we do, we're going to run this calculation on it. So as we read left to right, my hash equals my hash plus ord letter. That's short for ordinal. And what this does is it gets the ASCII number for each letter as we are looping through it. So there's an ASCII numerical value for each letter. And we're using that in this calculation. We're going to multiply it by 23. And the reason for that is 23 is a prime number. You can plug any prime number in here. And the real key to this is this modulo operator. So if you haven't seen this before, modulo gives you the remainder when you divide. So if you do modulo with the length, remember the length is 7. So if you divide any number by 7, the remainder is going to be anywhere from 0 to 6. And 0 to 6 is exactly our address space. And then after we get done calculating all of this, we are going to return the number, and it's going to be 0 through 6, and that will be the address that we use to place the key value pair in the hash table. So that is our hash method. So let's go take a look at both of these in VS Code. So that's where we create our hash table, and there's our constructor, and this is our hash method that we just created. And then here I've created a print table method just so we can print out the hash table. So I'll create a hash table here called my hash table, and then we will print out that hash table with this line down here. So I will run this, and those are our addresses there, 0 through 6, and each one of those contains none. And that is our hash table constructor. Now let's set a key value pair in our hash table. So let's bring up the two things we created in the last video, which is our address space, which we created with the constructor, and then our hash method. We're going to call our method setItem. The setItem method is going to use the hash method on the key to create the address, and then it's also going to create this key value pair in a list, and then watch how this key value pair goes into that address space at the value of 4. There's going to be a separate list at the address of 4 that this key value pair goes into. So for now, I'm going to remove this, and let's start building out the method. We're going to call it setItem. We're going to pass it a key and a value. So the first thing we need to do is figure out the address where we're going to store our key value pair. So we're going to have a variable that we call index. We're going to set it equal to self.hash. We're going to pass that method the key. Then it will compute the address. In this case, it will be 4, and that's where we will store our key value pair. So the next thing we have to do is initialize this empty list at that address. And we'll do that like this. We'll say self.datamap at that index, the index of 4. We're going to set that equal to this empty list. This is something that we only want to do if that empty list has not already been created. So we'll create an if statement here above this to say if at that address, if it is equal to none. See, all of the addresses are initialized to none. And if it is none, we need to initialize this with that empty list. Now that we have that empty list created, we can put the key value pair into that empty list. So we'll say self.datamap at that index. Then we're going to do a dot append with the list that contains the key and the value. So in this case, the key and the value will be bolts 1400. That goes right in there. So now let's walk through this, putting another key value pair in at the address of 4. So we're going to call the setItem method, pass it the key and the value. We're going to do this to get the index. It will be the index of 4. But this if statement, now at the index of 4, it is not equal to none, which means we are not going to create this empty list because it's already been created. Then the next step is we're going to append that key value pair. In this case, this is going to be washers with a quantity of 50, and that goes right in there. Now let's just add one more, lumber with a value of 70, so we have something at another index like that. And that is our setItem method. So we'll look at this code in a moment, and we will also create these key value pairs, put them into the hash table, then we will look at the hash table to make sure that everything got put in correctly. So now let's flip over to VS Code. So there is our setItem method there. This creates our hash table, and this puts in the 3 key value pairs that we just looked at. And this will print out our entire hash table to make sure that we have everything put in there correctly. So I'll run this, and there we have bolts and washers at the index of 4, and we have lumber at the index of 6. And that is our method for set. Now let's do our get method. Let's bring up our address space, and we'll have a couple of key value pairs in there, bolts and washers. And then we'll bring in our hash method like that. And we'll say get item washers. So we'll run this through the hash. That gives us an address of 4. We go to that address, we'll loop through the key value pairs till we get to washers, and then we'll return the value. If we have something like get item lumber, that's going to be at the address of 6. We come down here, that doesn't exist. So in this case, we're going to return none. All right, so let's shrink this down and write our method. So we'll say get item, we're going to pass it a key. Then we need to figure out the index for that key. So index equals self.hash. We pass this a key. We run that method. In this case, we're looking for washers, and we know that that's at the address of 4. So we only want to look for washers if there are key value pairs at that address. So we're going to say if self.datamap at that index is not none. So in this case, at the index of 4, we have key value pairs, but at the index of 6, we do not. There's no point in looking for something if the item we are looking for is at the index of 6. Once we know there are items there, now we can loop through them. So we're going to say for I in range of the length of self.datamap at that index. It is not the list that is the datamap going 0 through 6. It is this list here that is at the index of 4. And we're looking for washers in this case. So to see if we have a match, we're going to use this if statement. So let's walk through this. If self.datamap at that index, that's this same thing here, which was this list. Then we move to the I. The I is the I from the for loop. In this first iteration, that is 0. So the item that's at the index of 0 at that list is this key value pair. So then we want to look at that key, bolts. That is at the index of 0. So bolts, does that match the key, the one we passed to the method? In this case, the answer is no. So we come back and run the for loop again. So now I is 1, and that is this key value pair. At the index of 0 inside of that key value pair, that is washers. That is a match for the key that we're looking for. So we will return self.datamap at that index at I, but the next index over is the value 50. And then the other possibility, of course, is that we are looking for a key that is not in the hash table. So in that case, we're going to return none. And that is the entire method for getItem. So we'll look at this in a moment in VS Code. We'll create these two key value pairs. And then what we'll do is we'll do a getItem for bolts and washers. That should print out 1400 and then print out 50. Then we'll also do a getItem for lumber, which is not in the hash table, and that should return none. All right, let's flip over to VS Code. Okay, there is our getItem method there. This creates our hash table called myHashTable, and we'll add bolts and washers to the hash table. And then down here, we have 3 print statements, and each one of them is a getItem, one for bolts that should return 1400, one for washers that should return 50, and then one for lumber, which should return none. So I'll run this, and that returns 1400 and 50 and none. And that is our method for get. Now let's create our keys method. And what we're going to do with this is we're going to take all of the keys out of the hash table, put them into a list, and then return that list. So in order to do that, we're going to need a for loop that goes through our data map list and then moves across to see if there's anything in any of these addresses until it gets to an address where there is something there. And then we'll have another for loop that loops through the keys in this list. All right, so let's start writing this code. We'll say keys, and then the first thing we'll do is create that list that we're going to put the keys into. I'll just call it all keys. Then we'll create the for loop that moves through the data map list, the 0 through 6. Then we'll create a second for loop to go through this list here. So we'll do that like this. Notice it's almost identical to the one on top, but we've added this here. So that creates our 2 for loops, but this second for loop, we only want to run it if there is something at the address. So take, for example, the index of 0 down there. There isn't anything there. 0 is none, so we don't want to run this for loop. So we're going to say only if there is something there. If it is not none, only then do you run that for loop. Then we just need to write the keys to the all keys list that we created. So we'll say all keys.append, and then we'll take the particular key that we're looking at as we're going through these for loops, and then we will add it to that list. Then the only thing left to do is to return that list. Okay, so that is our code for the keys method. So let's flip over and take a look at this in VS Code. So there's our keys method there, and this is where we create our hash table. And then here we'll add bolts, washers that we saw before. I'm adding lumber in this case. Then down here we'll say print myHashTable.keys, and that should return that list with the 3 keys in it. Okay, so I will run this, and there's our list with bolts, washers, and lumber. And that is our method for keys. Okay, so now let's look at hash table big O. I'm going to bring up a hash table like this. I'm going to use linked lists instead of the nested list that we've done so far. And the only reason I'm doing it this way is it's visually easier to look at. And I'll bring up our hash method here. So since everything we do with the hash tables involves using this hash method, the first thing we need to do is figure out the big O of the hash method itself. So for a given key of a certain number of letters, it will always be the same number of operations to calculate the hash. That means that the hash method itself is O of 1. So now let's look at setting an item. We run it through our hash method, and let's say that's going to be at the address of 2. We append that onto our linked list like that, and appending that is also O of 1. Now let's look at get. We'll say get item screws. That's going to give us the address of 6. It was O of 1 to find the address, and then 1 operation to find screws. But what if our hash table looks something more like this? Now when we say get item screws, it's O of 1 to find this address, but then we need to iterate through the list until we get to screws. So it would seem that the worst possible scenario would be that all of these items would be put at the same address, and we would have to iterate through all of them, and it would be O of n. But the assumption with a hash table is that the distribution is going to be more like this. Even with the very primitive hash method that we created, it gave us a very good distribution of these items. The hash method that's built into Python is going to be even more efficient at distributing all of these items. And also, you're going to be dealing with a much larger address space. So collisions are going to be fairly rare. So we treat hash tables, which are implemented as dictionaries in Python, as O of 1. And it is O of 1 to place a key value pair or to look up something by key. Either way, it is O of 1. And that is our quick overview of hash table big O. So in this video, we're going to go over a very common interview question. So you may not see exactly what we're going to go over here, but a very high probability that you'll see some version of this. So we're going to bring up 2 lists. So what we want to determine is whether these 2 lists have an item in common. And obviously they have an item in common, the 5. And we're going to look at 2 approaches for how to do this. An interviewer will want to see the second approach. So the first approach, the obvious approach, what we would call the naive approach, would be to create nested for loops. So we'll have one for loop to go through the first list, then a second one to compare all the items in the second list to that number. So we'll see if that's equal to 1, and if that is or that is, then we'll iterate the first for loop and move that over 1. And then we'll go through the second one again. Then we iterate the first for loop again, go through this, and finally find a match. And because these are nested for loops, this is O of n squared. So let's just move these down here and we'll build this code quickly. This should be pretty easy at this point. So we'll say item in common, and then we'll pass it to two lists. Then we'll have a for loop that goes through list 1, another for loop that goes through list 2 that is nested inside of the first for loop. And if at any time I equals j, we'll return true. And if we go through the for loops and we don't find a match, then we'll return false. So let's flip over to VS Code and take a look at this. So there is our function there. These are the two lists that we just looked at. And then down here, we'll print out item in common and pass it to two lists. So I'll run this, and that returns true. And that's what we expected, because we do have an item in common, the 5's here. And then if we come up here to list 2 and change the 5 to a 6, like that, and we run it again, now it returns false. All right, so let's flip back. So that is the way to do it. That is the inefficient way. Now we're going to create the more efficient way of doing this. And as you may have expected, we're going to use a dictionary, since this is the hash table section. And what we're going to do is loop through the first list. We'll take the 1 and put it into the dictionary. We'll just make the value in this key value pair true. And we'll do the same thing for the 3, make that true. And 5 is the key, true is the value. And we have 3 key value pairs. So we had to loop through that first list. That's O of n. Now we will loop through the second list to compare the 2 to the dictionary, to see is the 2 in the dictionary. So every time you look for an item in a dictionary by the key, it is O of 1. Then we'll do the same thing for the 4, and then we'll do the same thing for the 5. And of course, this gives us a match. So we had to go through each list once, which you could say is O of 2n, but of course we drop the constants, and it is O of n. And O of n is far more efficient than O of n squared. So this version is what an interviewer is looking for. So now let's look at how to code this. We'll start this out the same. We'll call it item in common. We'll pass it to two lists. But the first difference is we need to create that dictionary. So we'll say my dictionary. Then we'll run the for loop to go through the first list. Then we'll take the values from that and put it into the dictionary. Then we'll have a second for loop. And the key here is that this is not a nested for loop. They are one after the other. So we'll just say if j is in my dictionary, we'll return true. If we go through the second for loop and we don't find any matches, we'll return false. So let's go take a look at this in VS Code. So there is our new updated version of the function that uses the dictionary. We have the same two lists here, and then we'll print item in common with list 1 and list 2. So let's run this, and that returns true. And we'll come up here like we did on the other one and change the 5 to a 6, and we'll run this again. And now that returns false. So you can see that both of these ways of writing this work, but the second one is far more efficient. So writing it the way that is more efficient is the real interview question. Okay, now let's look at graphs. We're going to start out by bringing this up. This is called a vertex or a node. The proper way to say it is vertex, but you'll hear the word node. And we'll bring up another vertex. The plural would be vertices. Then between the vertices, we have what is called an edge or a connection. The proper way to say it is edge. So we have vertices and edges. Let's bring in another vertex like this. So this vertex can have an edge with this vertex, or it can have one with this one, or it can have one with both. There is no limit to how many other vertices that a vertex can connect to. So now that we have a small graph, let's look at a couple of concepts. Let's say you want to go from this vertex to this vertex. Well, when you look at this, you would say that you don't want to go this way because that is 2 hops and this one is 1. You'd want to go the more direct route. But with graphs, one of the things you can have, you're not always going to have, but you can have, are weighted edges. So where you would use something like this would be in a Maps app. You're using Google Maps and the road between 76 and 82 has a lot of traffic, so you go this way instead because this has a cost of 5 and going this way has a cost of 15. Another place you'll see something like this is with network routing protocols. It would be better to have an extra router hop and have 2 very fast links than to go the way with a very slow link. And like I said, the edges can be weighted or not weighted. So another concept with graphs. We'll explain this with a Facebook connection between you and a friend. So with a typical Facebook account, your friend is friends with you and you are friends with your friend. It is a bidirectional relationship. So in a graph where all of the edges are bidirectional, you'll often see it like this without arrows. And when you see it like this, it is assumed that it goes both ways. So let's compare this to something like Instagram or Twitter when you follow a celebrity. You are following the celebrity. They don't follow you back. That is directional. So the edges can be weighted or non-weighted. They can be directional or bidirectional. Also, we have seen a graph in this course. It was a tree. Trees are a form of graphs, but they have the limitation that each node can only point to 2 other nodes. And when we looked at trees, we had mentioned that we had seen a tree before, which was a linked list. So linked lists are a form of a tree, and a tree is a form of a graph. Therefore, a linked list is a form of a graph, with the limitation that they can only point to 1 other node. But we typically think of something that looks like this when we think of graphs. So there are 2 ways we're going to look at being able to represent a graph. The first one is going to be an adjacency matrix. The other one will be an adjacency list. So let's bring up a graph and we're going to represent this in an adjacency matrix. So we'll start by looking at this A vertex. It has 2 edges with E and B. So we'll say A has edges with B and E. And we'll just put 1s in those boxes there. And of course, A cannot have an edge with itself. So we'll put a 0 in that one. And then it does not have an edge with C and D. So we'll put 0s in there. Now let's look at B. It has edges with A and C. So B has edges with A and C, and the rest will be 0s. So I'll just finish building this out like this to complete our matrix. So this axis represents the actual vertex. This axis is the items it has an edge with. So now one of the things that's interesting about an adjacency matrix, we had mentioned that A can't point to A. Well, also B can't point to B, and so on. You're always going to have this 45-degree line of 0s. And if you have a bidirectional matrix like we have here, you will always have a mirror image on each side of this 45-degree line that looks like that. But this is only if these are bidirectional. So let's change one of these to directional and take a look at that. We have a connection between A and B. So in the matrix, that is A connects to B, that's 1. B connects back to A, that has a 1. But if we remove the edge that points from B to A, and we change this to a 0, now we have lost our symmetry across that 45-degree line. So let's change the edge on the graph back to being bidirectional, and then we'll change it in the matrix, and now it is symmetrical. So another thing that you can have with your edges is that they can be weighted. So if they're weighted in an adjacency matrix, we will just store these weights in the matrix like this instead of having 1s. Okay, let's put that back. And that is our quick overview of an adjacency matrix. So now let's look at creating an adjacency list. That's just going to be a different way of representing this graph that we just looked at in the last video. And with an adjacency list, we're going to represent this with a dictionary. Let's start with our A vertex. It has edges with B and E, and we'll represent this in our dictionary like this. A is the key, and we'll have a list for the value in our key value pair in the dictionary, and that list will hold all of the edges that A has with other vertices. So now let's start moving around this circle here. So we'll look at B. It has edges with A and C. C has edges with B and D. D has edges with C and E. And then finally, E has edges with A and D. So now this adjacency list on the right represents the picture on the left. And an adjacency list is what we're going to use to create our graphs in this course. And that is our overview of an adjacency list. Now let's look at graph big O. So I'm going to bring up the same graph that we've used in the last couple of videos here, and we're going to represent this graph with an adjacency matrix and also an adjacency list. These are 2 different ways of representing that graph. So the first thing we'll look at is space complexity between the 2 of these. So with an adjacency list, we represent the vertex A like this, and then the edges it has with B and E. So we represent those in the adjacency matrix with those items I just highlighted in green. So a huge difference between an adjacency list and an adjacency matrix is that in a matrix, each vertex has to store all of the vertices it is not connected to. We have to store all these 0s. So from a space complexity standpoint, the adjacency matrix is the number of vertices squared, where the adjacency list is the number of vertices plus the number of edges. So now let's bring back our graph. So now let's look at the big O for the common operations that we're going to do with a graph. First, we'll look at adding a vertex. And this is just the vertex. We're not connecting it to anything. We haven't added any edges. So let's bring these back up. And with an adjacency list, adding that vertex, you just do it like that. Very simple. With an adjacency matrix, this is much more complex. Adding a new row, adding a new column. In fact, it is O of the number of vertices squared. You're basically rewriting the entire matrix. But with the adjacency list, it's O of 1. So this is a huge difference between the adjacency matrix and the adjacency list. So now let's bring our graph back. And what we're going to do next is add an edge. So let's bring these back up. And adding an edge, in this case it was between F and B, is we append an F here, we append a B here. Pretty easy. With the adjacency matrix, we change that to a 1. We change that to a 1. So in this case, both of these are O of 1. Now let's bring back our graph. The next step will be removing the edge between B and F. So let's bring these back up. So to remove the edge between B and F, we're going to go to B, and then we're going to go through that list of all the edges, find the F, and remove it. Then we're going to come down here and look for all the edges here that are B, and remove that. With a matrix, we're going to change that to a 0. We're going to change that to a 0. So to compare these, the matrix is O of 1. This is a win for the matrix, where the list, we're having to iterate through the list of edges that's associated with each one of those vertices, so it's O of the number of edges that we have to go through. So let's bring our graph back here. And the next thing is we're going to remove the vertex. So let's bring these back up. So if we're going to remove a vertex, it looks simple that we're just going to do that. But we also have to remove all of the other edges. So the vertex A could have an edge with F, so we have to go through this list. Then we have to come down to the next vertex and then go through this list. In other words, we're going to need to touch everything in this dictionary. With a matrix, in order to remove that vertex, we have to do this, which is basically rewriting the entire matrix. So the matrix is going to be the number of vertices squared, where the list on the right is the number of vertices plus the number of edges. Now with the adjacency list, if you have bidirectional connections, there's an efficiency in how you can write your method that makes this more efficient. Okay, so let's focus in on this matrix and make another point about this. We had mentioned earlier that we're not only storing the ones, we're also storing the zeros. And this is not a big deal when you have a small graph. But imagine that you're Facebook, and let's just say for easy figuring, you have 1 billion users, which is 1 billion vertices. So each axis, the horizontal axis and the vertical axis, are going to be 1 billion items. Even if each person on Facebook has 1,000 friends, you are going to be storing 1 million zeros for every one. So it's incredibly inefficient from a storage perspective. Whereas with an adjacency list, we don't have to store all of those zeros. So this is what we're going to use in this course. It is much simpler. It is much more efficient. And that is our overview of graph Big O. Now let's create the add vertex method. And all we're creating here is this. In the next video, we'll create our add edge method, and then we'll be able to do things like this. But for now, this is all we're creating. So when we add the first vertex into the graph, it's going to look like this. So let's bring this down here, and we'll create this. So we're going to say class graph. So the first thing we need to do is create a constructor. So I added this into the add vertex method because this is a pretty simple constructor. So it'll be like this, and then we create a dictionary. I'll call mine adjacency list, and it's just an empty dictionary. So it didn't make sense to create a separate video for that, so I went ahead and just added it here. But what that creates is this. And then the add vertex method is going to be the part that does this. So now let's create that method. So we'll say add vertex, and we're going to pass it whatever value we want that vertex to have. Then we'll add that as a key to our adjacency list and set it equal to an empty list. But there is a step we need to do before this line of code, because we don't want to have duplicates in our graph. So to walk through this line here, if vertex not in self.adjacencylist.keys. In other words, if the vertex isn't already in our adjacency list, only then are we going to add it. And then we'll return true that we were able to add that. And if this if statement equates to false, we'll bypass all of this and return false. All right, now let's go look at this in VS Code. So there is our class graph, and this is our constructor here. I also created a method to be able to print out the graph here. And this is the add vertex method that we just created. So I'm going to scroll this up, and this is where we create our graph. We'll call it my graph, and then we'll say my graph.add vertex with the letter A. And then with this line here, we will print out that graph. So I'll run this, and you can see our new vertex A with an empty list. All right, so that is our method for add vertex. So now let's create our add edge method. I'm going to bring up a couple of vertices like this. We're going to represent them like this, and we're going to connect these two vertices. And we're going to do that by doing this. So let's move this down here and start writing our code. We'll say add edge, and we're going to pass it vertex 1 and vertex 2, the two vertices that we want to have an edge between. So to connect these two, we will say first self.adjacency list. At the vertex of 1, remember the value there is a list, and on that list, we are going to append vertex 2. That's going to look like this. And then we'll do it the other way. On this one, this is vertex 2. We're going to do a append onto that list. We'll append vertex 1 like this. So this is only something we want to do if both vertices exist. So let's say we're trying to do an add edge between the vertices 1 and 3. Well, we don't have a 3 vertex, so we can't add that edge. Both of these have to exist. So above these two lines of code, we will need an if statement. And this one's kind of long, but it's not complicated. So this is basically saying if vertex 1 and vertex 2 both exist, then we can create an edge between them. And when we do, will return true. If either one of them don't exist, this if statement will equate to false, and we'll skip past that, and then we'll return false. All right, so let's go look at this in VS Code. So there is our add edge method there, and this creates our graph called myGraph, and then we'll create two vertices, 1 and 2, and here is where we'll add an edge between those two vertices, and then we will print out the graph with this line here. Okay, so let's run this, and you can see that we have created an edge between 1 and 2. Okay, so that is our method for add edge. So now let's remove an edge. We'll bring this up, and removing an edge is removing that white line at the bottom between the 1 and the 2. And then, of course, what it's really going to look like is us doing this. So I'm going to bring this down to the bottom. I'm going to bring these back because this is what we need to remove. And we'll start our method like this. And we'll pass it two vertices that we'll call vertex 1 and vertex 2. And then we'll do this at that key of v1, which is going to be 1. We want to remove the vertex of 2 like that. And then we'll do that on the other one as well, where we remove vertex 1 like this. So we can only do this, though, if vertex 1 and vertex 2 both exist. So we'll need an if statement. And this basically says if vertex 1 and vertex 2 both exist as keys in the adjacency list, then we can do these next two lines. And if that conditional in the if statement is true, after we run these two lines, we will return true. Otherwise, we will return false. So we'll take a look at this in a moment in VS Code. And when we do, we're going to build this graph, and then we'll remove the edge between A and B just like that. All right, so let's flip over to VS Code. So there's our method there. And this creates our three vertices A, B, and C. This connects them all together. And then down here, we will print this graph out. So I'll run this, and that gives us our graph with A, B, and C, and they are all connected to each other. So I'm going to come down here. I'm going to paste this line in to remove the edge between A and B. So now I'll run this again, and you can see up here that the edge between A and B has now been removed. But the code as it is written here does not address one of our edge cases. And to show you what I mean, we're going to flip back. So this was our original graph. Now we're going to create a graph that looks like this. I'm just going to add a vertex D, but it will not have any edges with any of the other vertices. Then I'm going to run remove edge between A and D. So to look at that, let's flip back over to VS Code. So this is the same method up here. The only change that we have on this page versus what we saw before is we added the vertex D here. And then down here, the remove edge is between A and D instead of A and B. So I'll run this. And now we get this very long error. Okay, so I'm going to move this over so we can see this a little better. But you can see the problem here was with remove edge here. And then the error itself is a value error. So remember value error, we'll be using that in a moment. And the reason for that is it says list remove X. It is not in the list. So let me pull this back over here. So when we try to run this line right here, it said line 24 was the problem. We're trying to remove an item that is actually not in that list. So now let's flip back and look at how to fix this. So that is our method so far. What we need to do is this. We'll put a try in right here. So we're going to try to run these two. But in case we get an error, and specifically remember it is a value error, we want to decide how Python is going to handle this. So all we want it to do is ignore the error. So we'll say pass. And pass basically says ignore this and move on. And it moves on to the next line and returns true. So now let's flip back over and look at this in VS Code. So there is our new and improved remove edge method where we have our try and accept. And I'll scroll up here. And this is absolutely identical to what we saw before where we had the D vertex, and then we're going to come down here and try to remove the edge between A and D, even though D does not have any edges with any other vertices. So I'll run this, and now you can see that the code will run. Okay, so that is our method for remove edge. Now let's create our method to remove a vertex. So let's bring this up. We're going to remove the D vertex. But before we can remove that vertex, we have to remove all of the edges that vertex has with other nodes. And it is only then that we can remove the vertex. So let's bring this back, put our edges back like that. And this is what that graph will actually look like. So I had mentioned in the Big O video that there would be an efficiency that we could use in graphs that have bidirectional connections. And the efficiency is contained in this list. We know that if D has an edge with another vertex, that vertex also has an edge with D. So for example, right here, this edge that D has with A lets us know that A also has a connection back with D. So in a moment, we're going to create a for loop that just loops through this list. And the variable we'll use in the for loop will be called other vertex. So in this iteration of the for loop, other vertex is A, and we'll go through its list of edges and remove D. We'll cycle through the for loop again. Other vertex is B. We remove D from that vertex, and then we'll do that for C as well. And now that we've removed all the edges, we can come down here and remove this vertex. So let's say we had a situation where the graph had 1,000 vertices. We would only have to go to these 3 to remove edges with D. And that is a huge efficiency. So our graph now looks like this. We've removed the edges, and we have removed the node. Okay, so now let's start coding this. We'll say remove vertex, and we'll pass it the vertex that we're going to remove. And the first thing we need to do is make sure that vertex actually exists in our graph. And if it does, we will use this for loop to go through that list of edges associated with D. So then we'll go to that other vertex and remove the edge it has with the vertex that we're trying to remove from the graph. Okay, so this part here, once again, is going to do this. Other vertex is A, we remove the edge, and then we're just looping through this list of edges. Now that we're done with this, we can remove the vertex itself. We will delete the vertex D. And that's going to look like this. And now our graph looks like this. We do still have a couple of lines of code to add. If we have gone through this whole process here and removed all the edges, remove the vertex, we will return true. If the conditional in this if statement equated to false, we will skip all of this and return false. So we'll look at this code in a moment in VS Code. And when we do, we will build this graph, and then we will remove D, and then we'll print it out. And when we print that out, it should look like this. All right, so let's flip over to VS Code. So there is the remove vertex method there. And I'm just going to scroll this up, and then I'll move this over so we can zoom in on this. So we'll create a graph called my graph. And these lines here create our 4 vertices, A, B, C, and D. And these create all of the edges that we had in the diagram, and this will print out our graph. So I'll run this, and that gives us our graph before we have run the remove vertex method on the D vertex. So I'm going to come up here, I'm going to paste in this line of code, and that's what's going to remove our D vertex. Then we will print this again, and D should be gone, as well as any edge that connects to D. So I'll run this, and this is exactly what we would expect. All right, that is our method for remove vertex. Now let's look at recursion. And if you haven't seen recursion before, this is a topic that typically takes a few times looking at this for it to really start to click. So what is recursion? My favorite definition of recursion is that it is a function that calls itself until it doesn't. So now let's look at a very common example that's used to explain recursion. I'm going to bring up a gift box here, and we need to open the gift box. And the way we open gift boxes is with the open gift box function. And when we run the open gift box function, it's going to return either a ball, in this case, or it's going to contain a smaller gift box. And if it's a smaller gift box, the way we open gift boxes is with the open gift box function. So we'll run that again. And when we do, that gift box is either going to contain the ball or it will contain a new, smaller gift box. So now we're going to run the open gift box function again. And in this case, we'll just say that we found the ball. Okay, so now let's put this back and we'll look at some code. Now I want to emphasize this is pseudocode. This is not code that will actually run. It's just for example. So we're going to create our function, open gift box. And we're going to say if when we open the box, it contains a ball. So if ball, we will return that ball. Otherwise, it's a gift box, in which case we need to run the open gift box function. And this is where the function calls itself. So there are a couple of things about recursion that are very important. First, the process of opening each new box is the same, or the process of whatever we're doing with recursion has to be the same. The other key point is each time we open a box, we make the problem smaller. So now let's walk through this code with our boxes. So we'll say open gift box, and when we do, we'll check to see, is this a ball? In this case, it's not, so we have to run the open gift box function again. So it calls itself. So this is a second instance of the function that we're putting on the call stack. And we'll talk about call stacks further in the next video. So then we're going to check to see if this box contains a ball. It does not. So we have to run another instance of open gift box. This is going to call itself again. So now we run another instance of the function. Now, when we check to see if it's a ball, it is a ball. And because this is a return, we will not run this line of code and we stop having the function call itself because we have this return method here. So you have to have this in your recursive function. So now let's put this back again and talk about a couple of concepts here. When we open this box and it contains the ball, this is what we call our base case. This is when we are going to stop opening boxes or the function will stop calling itself. If it needs to call itself again, this is called a recursive case. This is also a recursive case, and this is the base case. Let's bring our code back in here. When this if statement is true, that is our base case. And it's very important to have this because if you don't, we'll remove this, the function gets called, and then it calls itself, which creates another instance of the function, and that's going to call itself, and then we create another instance of the function, and so on. And this will create what is known as a stack overflow. So you have to have a base case where this will at some point stop calling itself. And there are a couple of things about this that are very important. First, this if statement has to be true at some point. So you can't have something like this, because 1 is never greater than 2. This will never be true, and you will loop through this infinitely and create a Stack Overflow. And you might be saying, well, that's pretty obvious that 1 is never going to be greater than 2, but sometimes we have if statements in our code that are very complicated, and it's not obvious that the if statement is not going to ever be true. So if you get a Stack Overflow in a recursive function, this is one of the places to go troubleshoot. So let's put this back. The other thing is that you have to have a return statement. If you have something like this that doesn't return anything, the if statement becomes true, you print hello world, and because it is not a return statement that causes us to stop running code, it just goes right to the next line, and we go right back into our loop and have a Stack Overflow. So it's very important that you have the return statement in your code. And that is our quick overview of recursion. So now the next thing we're going to look at is the call stack. And I'm going to start out explaining the call stack with functions that are not recursive. Then in the next video, we're going to look at how recursive functions go on the call stack. And the reason for that is because it's a lot easier to understand what is happening on the call stack first with non-recursive functions. So earlier in the course, we looked at a data structure called a stack, and we used the analogy of it being like a can of tennis balls. That all applies here as well. So whatever function is at the top of the call stack is the only one that can run. Once that function is done running and you remove it, then the next function can run. And when it is complete, that'll be removed, and then the next function can be run until that one is complete. So let's take this frame here and move it over, and we're going to use this for a call stack. So let's say we have a simple function called function1, and all it does is print out a string that says 1. Function1, when you call it, will be put on the call stack. It will print out that string, and once it's done running, we'll remove this from the call stack. So let's bring this back and look at something a little bit more complex. Let's say that function1, before it prints out this string, calls function2. When function1 calls function2 gets pushed on to the call stack. But let's say function2 is going to call function3. That will cause function3 to get pushed onto the call stack. And then we'll say that function3 doesn't call any other functions. It's just going to print out the string 3. So this gets printed out like this. And once it does that, function3 is done running, and we can pop that from the call stack. And now function2 is at the top of the call stack again. Function2 was waiting for function3 to finish before it could go to the next line in function2. So now function2 can print out the string 2. And once it does that, we can pop function2 from the call stack. And function1 was waiting for function2 to finish before it could run this line of code and print out the string 1. And once that's done, function1 can be popped from the call stack. So notice that we call these functions in the order of 1, 2, 3, but it printed out 3, 2, 1, because 3, 2, 1 is the order that these came off of the call stack. So let's bring this code up here again, and let's go look at this code in VS Code. So there are the 3 functions there, and this is where we call function1 to kick all of this off. And what we're going to do is we're going to come up here to this button here that says run and debug. When I hover over this, I'm going to click on this. It'll bring up this side window here. And then over on this side, there are the 3 dots here that say additional views. I'm going to click on this, and I'm going to choose debug console, just like that. And then in the middle here where it says function1, next to the line number, you can see that I get a red dot when I hover here, but when I click, that becomes a bright red dot. That's going to create a breakpoint. And you can see that down here, and you can see the line number 13 is where that breakpoint is. So I'm going to shrink this down. And then up here we have variables. I'm going to close that, and watch, I'm going to close that. And we're just going to focus on call stack here. And where it says run and debug up here, make sure it says Python current file. If you pull down on this, there can be other things that you can choose. Just make sure Python current file is chosen. And next to that, we have the green play button. I'm going to click on this. You can see that function1, where we created our breakpoint, is highlighted. That will be the next line of code that will be run. And if you come up here to the top, there's a downward pointing arrow here, and it says step into. This is what I'm going to use to step through this code one line at a time. And then we can see how everything is going on in the call stack and how it's going to print out. So when I click on this, this will call function1 and add it to the call stack. So I'm going to click on it, and you can see over here that function1 is on the call stack, and now we're running the code in function1. The first thing function1 does is call function2. So I'm going to click on this, and now function2 has been added to the call stack. And the first thing that function2 does is it calls function3. So I'll click on it again, and now function3 has been added to the call stack. So you can see up here that print the string 3 is highlighted. So when I click on this button again, it's going to do 2 things. It's going to print out the string 3, and then function 3 is going to be popped from the call stack over here. So I'm going to click on this, and function 3 has been popped from the call stack, and 3 has been printed out. Function 2 is waiting for function 3 to complete for it to move to the next line of code where it says print 2. And when this runs, 2 is going to be printed out to the console, and function 2 will be popped from the call stack, like that. Function 1 was waiting for function 2 to finish before it could move on to the next line and print out the string 1. And when I click on this again, 1 will be printed out, and function 1 will be popped from the call stack. So I'll do that now. And now we have 3, 2, 1 over here in our debug console, and our call stack no longer has any of those 3 functions. All right, and that is our overview of the call stack. So now we're going to use recursion to solve a factorial. And factorial is something that is used to teach recursion in pretty much any course that teaches recursion. And if you've never seen a factorial before, it looks like this. This is 4 factorial. And 4 factorial is 4 times 3 times 2 times 1. So I'm going to shrink this down like this, and let's walk through why this is a perfect thing to use to teach recursion. So 3 times 2 times 1 would be equal to 3 factorial. So you could say that 4 factorial is equal to 4 times 3 factorial. And you could say that 3 factorial is equal to 3 times 2 factorial, and 2 factorial is equal to 2 times 1 factorial, and 1 factorial, well, this is our base case, so this one's going to be different. 1 factorial is just going to be 1. A couple of videos ago, we talked about a couple of things that you need to have in a recursive function. The first is that you need to be doing the same thing over and over. And you can see that this process is the same all the way down. The other thing is that the problem needs to be getting smaller until you finally get to a base case. So this is perfect. So I'm going to shrink this down. And what I'm going to do is I'm just going to bring in the entire function, and then we'll walk through it. So this is our recursive function for factorial. We're going to pass this a number n. In this case, we're going to pass it the number 4. Then we're going to check to see if n is equal to 1. When we get to the point where n is 1, we're going to return 1. If n is not equal to 1, we'll come down to this line here, where we return n times factorial of n minus 1. So this is where the function calls itself. So in this first iteration, it would look like this. We're going to return n, which is 4, times factorial of n minus 1. N minus 1 would be 3. So let's move this function up to the corner like this, and we'll walk through this. So first, we have factorial of n. N is equal to 4 to begin with. And we'll say, is n equal to 1? Well, obviously, it's equal to 4, so it's not 1. So we will return n times factorial of n minus 1. So we can do this, and we'll populate that with 4 and 3. So now we're calling the function with n being equal to 3. So when we run our if, is n equal to 1? It is not. So that causes us to run this line here. And this is going to be 3 and 2 this time. So we're running factorial on 2. So now our if statement is n equal to 1. It's not. So we have to run this line again. And now we're going to use 2 and 1. So we're running factorial on 1. So now when we say if n equals 1, it is going to be true. And we're going to return 1. That is this 1 here. So now let's just look at these lines here. Let's spread these out. And when we return the 1, we're returning the 1 to this function call here. And then we're going to return 2 times factorial 1 to this function call, and so on up the line until we return the answer to this line here. So let's walk through what this is going to look like. So when we return 1 there, we're returning 2 times 1, which equals 2, up to here. Now we're going to return 3 times 2, which equals 6, up to here. Now we're going to return 4 times 6, which equals 24, up to here. And factorial of 4 equals 24. So now let's look at this a different way. Let's use the gift boxes that we used a couple of videos ago. So we start out with this being factorial of 4, then 3, and 2, and 1. And in the gift box video, we had a ball when we reached our base case, but now this is going to be a 1. And then 1 gets returned to this function call. And then we have 2 times 1 is 2, gets returned to this function call. 3 times 2 is 6, like that. And then finally we get to the 24. And now let's look at this yet another way with our call stack. We start out with factorial 4. That goes onto the call stack first. Then we have factorial 3 gets pushed onto the call stack. And then 2 gets pushed onto the call stack. And then 1 gets pushed onto the call stack like this. And it's only that last instance of the factorial function that can run because it's at the top of the call stack. So remove that, and then we can calculate the next one like this, and so on until we get to here, and then we return the 24. So now let's go look at this in VS Code. So there's our factorial function there, and then we'll call it here factorial 4 and print out the result. And just like we did in the last video, we're going to come up here and open this run and debug side window like that. And then over here, we're going to click on the 3 dots, and we're going to choose the debug console. And next to this line, we're going to click the red dot, highlight that to create a breakpoint. Up here for run and debug, we want Python current file to be here. And if it's not, do the little drop down menu, make sure that's selected, and we'll click on the green play button. And now we can walk through this step by step. So now when I click on the step into, it's going to run factorial, the factorial function, with a value of 4, and that gets pushed onto the call stack. It's going to check to see if n is equal to 1, and obviously it is not, so it's going to come down here. And when I click on this again, it's going to push factorial onto the call stack again, this time with the number 3. So notice that both functions on the call stack are named factorial. And that's why I did the call stack video I did in the last video. It's easier to keep track of this and kind of see what's happening when the items on the call stack are called function 1, function 2, function 3. In a recursive function, it's just going to be called factorial because it's calling itself. But these are distinct instances of factorial. So I'm going to come up here and we'll step into this again. The if statement is going to be false because n is not equal to 1. We'll come down here. And now we're going to get another factorial pushed onto the call stack over here. You can see we have 3 of them now. This latest one is with the number 2. N is still not equal to 1, so we're going to come down here again. And now it's going to get pushed onto the call stack with the number 1. Now we have 4 factorials on the call stack. But this time, n is equal to 1, so we come down to the return 1 here. And when it returns that 1, it's going to pop one of those factorials off the call stack. So I'm going to click on this, and you can see that we only have 3 factorial functions on the call stack now. And as I showed before in the animations, it's returning it here. It is returning it to where this was called with the number 2. So when I click on this, that's going to get popped from the call stack. And this is going to be with the number 3, and with the number 4. This will be the final one that gets popped off the call stack. And it's going to return that value to here. And so for this last one, I'm going to move over from the step into a couple of buttons over to where it says continue. And when you click on this, it'll just run the rest of the code. I'm going to do this because there's a message that will pop up otherwise. So I'm going to click on this, and you can see that we have the number 24 that's been returned. And that is our recursive function for factorial. All right, now we're going to look at our first sorting algorithm, bubble sort. And in this video, we'll walk through the logic of how bubble sort works. And in the next video, we'll write the code. So we're going to sort this list, except I'm going to change it to look like this so we can visually see the size of the numbers. And previously, I had shown lists to be in green. And what I'm going to do here is I'm only going to show these to be in green once they're sorted. So I'm going to move this back. And with bubble sort, what we're going to do is we're going to start with the first item in the list, and we're going to compare it to the second item. And if the first item is larger than the second item, we're going to switch these. Then we'll take the second item and compare it to the third item. And in this case, these don't need to be switched. So we'll go to the third item and compare it to the fourth item. These do need to be switched. And the fourth item with the fifth item, and the fifth item with the sixth item. And now that 6 is sorted. What we've done is we've bubbled up the largest item. So in order to do this, we had to do 5 comparisons. We had 6 items, and we did 5 comparisons. Now we only have 5 items left to sort. So in this round, we'll only have 4 comparisons. So we'll start back at the beginning and compare the first item to the second item. That doesn't need to be switched. The second item to the third item, the third to the fourth to the fifth. That's 4 comparisons. And now the second largest item out of the list has been sorted. It has been bubbled up. So let's just finish sorting these. We'll compare first to the second, second to the third, third to the fourth. Now that item is sorted. And then we'll compare first to second, second to third. And now the third item is sorted. And then we'll just compare these two. And if they need to be switched, they'll be switched. Otherwise, we know they are both sorted. And now we have a completely sorted list. So now I'm going to put this back the way it was. And this is where we're going to start in our next video when we code bubble sort. So now we're going to code bubble sort. And we're going to pick up where we left off in the last video with this list here. I'm going to shrink it down into the corner so we have room for our code. And we'll start writing our function, which will be called bubble sort. And we'll pass it a list. We'll call it my list. And that's going to be the list we have in the lower right-hand corner here. So remember in the last video, we talked about how the first time we would go through the list, there were 5 times we were going through the list. And then there was 4 times and then 3 times. So we're going to start out with this for loop, where the range is the length of the list minus 1. That's going to be equal to 5. And then we're going to go to 0, and then we're going to decrement it each time. So what we're going to do now is the second for loop is going to be the for loop that is moving forward through the list. So that's going to look like this. This one, to begin with, is going to run 5 times, do 5 comparisons. And then when we go through this again, I is going to be 4, and then this is going to run 4 times. So it's inside of this for loop where we're going to do our comparisons. So we'll have an if statement. We'll say if my list at the index of j is greater than my list at the index of j plus 1. So this is going to be the index of j in the first iteration, and this is going to be j plus 1. So if j is greater, we want to switch these two. And we'll switch these with these 3 lines of code. So let's walk through this. Temp equals my list at the index of j. So temp equals 4. Then on this line, j is equal to j plus 1. That's going to move that value of 2 over 1 like this. And we'll say my list at j plus 1, that empty spot, we want it to be equal to temp. And that moves that in there. And once we run through these for loops, we're going to have a list that looks like this. And the only thing left to do is to return the list. And that is our entire function for bubble sort. So I'm going to take this list and mix it back up the way it was. And now let's go look at this in VS Code. So there's our function there. And this is where we run bubble sort on that list that we just saw, 426513, and we'll print out the results. And I'll run this. And that gives us our list in order 1 through 6. And that is our function for bubble sort. Now let's take a look at selection sort. I'll bring up the same list that we use for bubble sort, and we'll look at it like this, just like we did before. But a difference that we're going to have here is that we also need the indexes for selection sort. So I'm going to bring these in. So with selection sort, we look at this first item, and then we're going to keep track of the index where the minimum value is. And since this is the only one we've looked at so far, this first item, we'll say that the minimum index so far is at the index of 0. So an important thing to emphasize here, min index is the index where the minimum value is. We're not storing the value, we're storing the index in this variable. Then we're going to have a for loop that starts at the next item over. And we'll say, is this value less than the item that's at the index of min index? In this case, min index is the index of 0. And in this case, it is. So now we're going to store this index here. And we're just going to move across. Is this one less? It is not. This one is not, but this one is. So we'll change min index to 4, and then we'll move to here. And we've gone all the way through, and the minimum index is at the index of 4. Then what we're going to do is we're going to switch these values. And when we do, that value of 1 at the index of 0 is sorted. I'll color that in green. So then we're going to move to the next item. And we're going to store that in min index, and we'll compare it with everything throughout the rest of the list. In this case, nothing is less than what we started with at the index of 1. And this is a special case that we'll have to code for when there's not going to be a swap. And we'll see that in the next video when we code this. So then we move to the next item. And min index is going to be 2. I'm going to take this min index and move it to the left like this because we're going to run out of room on the right there as we get all the larger items pushed over. And this next item will be less. So now the min index is 3. And this will switch it again. This one's even less. So min index equals 5. So we'll take that value at the index of 5 and swap it with the one we started with. And now that 3 is sorted. We're going to start out with this 5. That's at the index of 3. We'll compare it to the next one. That's less at the index of 4. This one is not less. So the minimum index is at 4. We'll switch these. Now that 4 is sorted. Then we move to this next one. Min index is 4. We compare it to this one. We don't need to make a swap here. These are both sorted. So it's worth noting that we don't have to do this a 6th time at the index of 5. We only had to do this at the indexes of 0 through 4. So I'm going to put this list back to the way it was like this. And we'll pick up here in the next video when we code selection sort. So now we're going to code selection sort. And this is where we left off in our last video. I'll shrink this down and we'll start writing our function. So we'll say selection sort, we'll pass it this list. And now the first thing we have to do is create a for loop to loop through the list. So if you'll recall from the last video, we only went through indexes 0 through 4, and once you do that, everything is going to be sorted. So we're going to do this for the range of the length minus 1. Now for our next line of code, I'm going to enlarge this. This is going to be I here, I from the for loop. And remember, we set min index to be equal to 0. Well, that's actually going to be I. So let's shrink this down and put this in with the rest of our code. Min index on each one of these loops through this for loop is going to need to be set equal to I. And once we do that, we need to compare the item at min index to all of the other items after that in the list. So we'll have a separate for loop for that looks like this. Because we're looking at everything after the index of I, we're going to start at I plus 1. So this is going to be our start value for our for loop, and this is going to be our end value. And remember, the end value, we are going up to, but not including this value. So the length is 6. That means we're going to go up to the index of 5. So let's enlarge the graph here and look at what that looks like. So for the first iteration, this is going to be I, and then j is going to be I plus 1. And min index is going to be equal to I, which is going to be the index of 0 in this case. Then we're going to compare that to the value at the index of j, and that one is lower, so we're going to set min index to be equal to j. But we're only going to set min index equal to j if the value at j is less than what we had previously stored at min index. So let's shrink this down and take a look at that. Let's bring our code back. We'll need an if statement that says if the item at the index of j is less than the item at the index of min index, then we'll set min index equal to j. So let's enlarge this again. And in this case, min index being equal to j means that it's equal to 1. And that second for loop is going to move the j through the list like this. And if we see another item that's less than min index, such as this, we'll set min index equal to j again, which in this case is 4. And then we'll continue to the end of the list like this. So now that that second for loop is done running, we know that min index equals 4, and we need to take the item at the index of min index and the item at the index of I and swap them. And once we do, that first item will be sorted. So let's shrink this down. And we'll be able to swap those two items with these 3 lines of code. I'm not going to walk through these because this is very similar to what we did in bubble sort to swap 2 items in the list. But there is a scenario where you don't want to run these 3 lines of code. And to walk through that, I'm going to enlarge this again. The second time through the first for loop, this second item is going to be I, and j will be I plus 1, so it'll be that next item over. And you can just look at this and see that the item at the index of I is going to remain the min index after we're finished. And that index is going to be 1, I'll put that up there. But that second for loop with the j is going to go through to the end of the list like this, and we don't have an item that needs to be swapped. So we have a situation where min index is the index of 1, and the index of I is equal to 1. So we know that the item at the index of I is sorted. I'll go ahead and color that in green, and I'll shrink this down and bring in those 3 lines of code that are used for swapping items. We don't want to run these 3 lines of code in this situation. So we're going to say if I is not equal to min index, only then do we want to run these 3 lines. In other words, if I and min index are equal, we don't want to run these 3 lines. Now let's put this in with the rest of our code like this. And if we run this code to completion, it will make our list look like this. And the only thing left to do would be to return the list. Now let's go look at this in VS Code. Okay, there's our selection sort function. And we're going to call that function here with that same list that we were working with before, and we will print the results. So I'll run this, and that returns a sorted list 1 through 6. And it looks like we have a working function for selection sort. Now let's look at how we do insertion sort. I'm going to bring up this list here. And with insertion sort, we always start with the second item in the list. And then what we do is we compare it to the item before it. If it's less than the item before, we're going to do this, and we'll drop that into the correct spot. Then we go to the next item, and we do the same thing. We compare it to the item before that. This one is not less than, so we don't move this one. This one, we compare it to the 6. We move this over. We compare it to the 4. It's not less than the 4. We drop that in. And then the 1, we're going to compare that to the 6, and the 5, and the 4, and then finally, the 2. We put that there. We drop this in. That was actually going to be a special case, the one that goes all the way to the beginning, and we'll talk about that when we code that. And then the last one here, we'll move this over until we finally compare it to the 2. It's not less than the 2, so that one goes there. And then once that 3 gets dropped in there, that's the last item, and that means that the entire list is sorted. In the next video, when we code this, we're going to start out with a list that looks like this. We're just going to swap these 2 items to make things a little bit easier so we don't have to walk through as many steps. And this is where we'll pick up in the next video when we code insertion sort. Okay, now let's code insertion sort. We'll pick up where we left off in the last video with this list. I'll shrink this down here, and we'll start writing our function. So we'll say insertion sort, we pass it this list, and we'll start out with this for loop. The range goes 1 to the end of the list, and remember, we're always going to start at the index of 1, that second item in the list. Then we're going to need a variable to hold the value of that item. So we'll say temp equals my list at the index of I. So we're going to compare that to the item before it. We'll call this j. Since that's the index before, we can just say j equals I minus 1. And because that 2 is greater than the 1, we're just going to put that there. The first time we have an item that is going to be less than the item before it is going to be this 3. So let's just skip ahead to that. And because j equals I minus 1, we'll put the j there. So we're going to have a while loop here that says while temp is less than my list at the index of j, the index of j is going to be that 4, and temp is going to be 3. So we're going to say while temp is less than my list at the index of j, and it is less than in this case, the first thing we're going to do is move that 4 over into that open spot. So we'll say my list, j plus 1 is equal to my list at the index of j. That moves that over. Then we want that 3 to be moved over into the index of j, like this. So we'll say my list at the index of j is now equal to temp. So the value at that index is now going to be equal to 3. Then we need to move that j over 1 to point at that 2, like that. We'll do that with this line of code. J minus equals 1, we'll decrement that by 1. Then we come up here and run the while loop again. So now is temp less than my list at the index of j. So in this case, it is not, and that's going to break us out of this while loop, and we'll just leave that index equal to 3. So there is an edge case that we need to talk about. I talked about this a little bit in the last video, and to explain that, I'm going to exchange the 1 and the 2 here, like this. And then I'll walk through what's going to happen with the code as it is written if we move that 1 over. So we would start here with the 1, j would be the item before that, and then we run through the while loop and say, is temp less than my list at the index of j? It is. So we'll move the 2 over, and then this line of code is going to move the 1 over, and then this line, j minus equals 1, is going to have j pointing at the index of -1. And this is where the problem is. You don't want this to keep moving over. You want the loop to stop as soon as j is ever equal to -1. So we need to add something to the conditional in our while loop. So we'll say, and j has to be greater than -1. And now because j is equal to -1, that breaks us out of our while loop. We stop running this code, and then we just leave that index to have that value of 1. So now all of that code works. The only thing left to do is to return the list. So now let's take this list at the bottom and unorder it again, and then we'll go take a look at this code and this list in VS Code. So there is the insertion sort function here, and then down here we'll run insertion sort on our list, and we'll print out the results. So I'll run this, and that gives us our sorted list 1 through 6, and it looks like we have a working function for insertion sort. So now let's look at the big O of insertion sort. And obviously we had a loop within a loop, so that's going to be O of n squared as our worst possible scenario. But our best possible scenario is when we have sorted or almost sorted data. So let's bring up our list that is almost sorted that we saw in the last couple of videos. And let's look at the number of operations to sort this. So let's look at this item here. Because it is already greater than the item before, it's not going to run that second loop that compares it to all the items before it. That one just gets left in place. Same is true with this one. This item is less than the item before it. We'll move that over and drop that in. And then for the rest of this list, we're going to go through it linearly. So if you have already sorted or almost sorted data, the time complexity for this is going to be n, not n squared. And you have to take that into consideration when you're looking at insertion sort, big O.